Hey everyone, tonight we're stepping out onto the Giza plateau, not to talk about pharaohs or curses or gold, but to stare at a single piece of granite that shouldn't exist. Forget aliens, forget fantasy. This is a story about measurements, about drill cores with spiral grooves so precise they look like they were cut yesterday in a modern machine shop, about 70-ton stone boxes polished smoother than glass. Before you settle in, take a moment to make yourself comfortable, and if you enjoy these late-night history wanderings, consider subscribing. And if you'd like, leave a comment telling me where you're listening from and what time it is where you are. It's always fascinating to see who's tuning in from different corners of the world. Now dim the lights, maybe put on a small fan just for that steady hum in the background. Now let's go back to 1883, to a man brushing sand off a granite core that would quietly unsettle a century of assumptions. In 1883, under a sky bleached white by the Egyptian sun, William Flinders Petrie crouched in the grit of the Giza plateau and brushed sand away from what looked at first like a broken fragment of stone. Petrie was not a mystic, not a treasure hunter chasing legend, but an engineer by temperament, a man who measured first and speculated later. The fragment in his hand was a cylindrical core of red granite, extracted long ago from a larger block during some ancient drilling process. It was not ornate. There were no hieroglyphs carved along its side, no ceremonial polish to distinguish it as sacred. Yet as he rotated it slowly between his fingers, something caught the light in a way that halted his breath. Spiraling around the surface was a continuous groove, a helical ridge wrapping from one end to the other with remarkable regularity. It did not wander, it did not deepen or fade randomly. It advanced in steady increments like the threading on a modern screw. Petrie did what engineers do when confronted with anomaly. He measured. He counted the spacing between ridges, noting the uniform pitch. He observed the depth of the groove and the smoothness of its walls. The spiral advanced into the granite at a rate that suggested a consistent feed, roughly 1/10 of an inch per revolution by his estimation, an astonishing penetration considering the hardness of the material. Granite ranks around 7 on the Mohs scale of mineral hardness. Its quartz crystals, harder than the copper tools Egyptologists insisted were the only implements available to Old Kingdom builders. Copper, soft and malleable, ranks around 3. In basic material terms, copper should not cut granite efficiently, certainly not in a way that leaves behind clean, evenly spaced helical striations. Petrie compared the core to experimental marks made with bow drills and abrasive sand, the accepted explanation for Egyptian stone drilling. The comparison unsettled him. Abrasive drilling with sand can indeed grind into granite, but it leaves a different signature. The action is chaotic at microscopic levels, the grains of quartz in the sand rolling and fracturing unpredictably under pressure. The resulting grooves vary in depth and spacing, reflecting the inconsistency of human motion and the irregular distribution of abrasive particles. What Petrie held in his hand told a different story. The groove did not wobble, its pitch did not drift. The walls of the cut bore parallel lines consistent with rotational advancement under constant pressure. In modern machining language, it resembled a feed mark, the trace left when a rotating tool advances into material at a steady, calibrated rate. Petrie recorded his findings carefully in his notes, describing the uniformity and the speed implied by the depth of penetration. He stopped short of declaring the marks impossible, but he made clear that they did not align comfortably with the prevailing narrative of simple copper tools guided by hand. The granite core became known simply as Core 7, catalogued and stored among other fragments that had been largely ignored before his attention sharpened them into significance. As additional cores surfaced from different excavation sites across Giza, the pattern repeated. Each bore spiral grooves of similar character, with consistent pitch and comparable depth. Engineers examining them decades later, with more refined instruments, confirmed Petrie's initial discomfort. Laser measurements revealed that the spiral spacing across multiple cores remained astonishingly uniform, separated by mere fractions of a millimeter. The feed rate implied by the groove depth suggested a level of pressure and torque, difficult to reconcile with hand-driven bow drills and copper tubes. The paradox is straightforward and entirely physical. To drill into granite efficiently, one must either use a tool harder than the quartz crystals embedded within it, or apply sufficient abrasive force in a highly controlled manner. Copper alone cannot meaningfully cut quartz. It deforms before it abrades. The standard explanation relies on quartz sand acting as the true cutting agent, the copper tube serving merely as a holder for the abrasive slurry. In theory, this could work given enough time and patience. However, time alone does not produce uniform pitch. Patience does not automatically generate consistent feed rates. Human arms fatigue. Pressure varies subtly with each rotation. Abrasive distribution changes as water carries grains away from the cutting face. These micro-variations accumulate, leaving behind signatures of inconsistency. The granite cores from Giza show surprisingly little of that drift. The spiral advances as though governed by a guiding mechanism, maintaining steady downward motion with each revolution. Modern engineers examining magnified cross-sections of the grooves have noted the presence of distinct striations within the larger spiral, fine parallel lines that suggest a cutting edge maintaining contact in a consistent orientation. This detail matters because it implies not just rotation but stability of alignment. A handheld tool, even with careful guidance, tends to chatter slightly under load. That chatter leaves microscopic evidence in the form of irregular microfractures and erratic striation angles. The core's Petri catalog display comparatively smooth internal surfaces, the marks tracking along predictable paths. This is not to say that ancient Egyptians possessed steel drills or diamond-tipped machinery in any conventional sense. There is no surviving evidence of such tools. Rather, the anomaly lies in the quality of the mark itself. The groove's mechanical appearance suggests process control. Process control implies repetition under standardized conditions. If multiple cores share near identical pitch and feed characteristics, the likelihood increases that the method employed was consistent across different drilling operations. That consistency is the first crack in the official story. The established narrative emphasizes immense labor forces and prolonged abrasion, describing a civilization that achieved precision through endurance rather than through advanced tooling. Endurance can indeed accomplish remarkable feats, but endurance does not automatically produce mechanical uniformity. Precision on the level observed in these cores implies either extraordinarily disciplined technique, refined over generations, or some method of stabilizing motion beyond freehand rotation. Early engineers who encountered Petrie's data were not inclined toward fantasy. They were trained to think in tolerances and material properties. When they compared the granite cores to contemporary drilling marks, they found uncomfortable parallels. The uniform pitch resembled feed rates achieved by lathes or rotary drills, advancing under mechanical constraint. The depth of cut per revolution appeared faster than what late 19th century steel drills could manage in granite without significant wear. That observation alone did not rewrite history, but it introduced doubt. If 19th century industrial tools struggled to achieve comparable feed rates in granite, how did Old Kingdom artisans manage such penetration with copper tubes and sand? Some argued that the measurements were misinterpreted, that the apparent depth per revolution might reflect overlapping abrasive action rather than true mechanical feed. Others suggested that the Egyptians could have used weighted drill rigs to maintain consistent pressure, though no physical remains of such rigs have been identified. The debate remained grounded in physics rather than mythology. It centered on torque, hardness, abrasion rates, and human ergonomics. The granite core itself did not speak of lost civilizations or impossible technologies. It spoke of geometry. Each spiral ridge followed the previous one with near mathematical discipline. The constant pitch meant that for every full rotation of the drill, the tool advanced downward by a predictable increment. That relationship between rotation and linear movement is fundamental to machining. In modern workshops, it is achieved through lead screws and calibrated feeds that ensure uniform penetration. The granite core suggests a similar relationship between rotational motion and vertical advancement, whether achieved mechanically or through some highly refined manual system. The first crack in the story was not that ancient Egyptians achieved the impossible. It was that they achieved something measurable that did not fit comfortably within the assumptions about their tools. Petrie's discovery did not overturn Egyptology, but it introduced a data point that required explanation rather than dismissal. Over time, the granite cores became reference artifacts in discussions about ancient precision. They were not grand monuments like the pyramids themselves, but small, almost forgettable fragments that carried disproportionate weight because of what they implied. Precision is rarely dramatic. It is quiet, expressed in tolerances rather than spectacle. The spiral groove on core 7 is subtle. One must look closely to appreciate its regularity. Yet that regularity challenges the simplicity of the narrative. It suggests that Old Kingdom builders may have understood drilling dynamics at a level not fully captured by surviving textual or material evidence. Engineers who revisited the cores with modern metrology tools confirmed that the spiral angles remained consistent along their length. The internal diameters of drilled holes from which the cores were extracted showed minimal tapering, indicating stable alignment during drilling. These observations do not require the introduction of advanced metallurgy beyond what archaeology supports. They require only the acknowledgement that the process used was more controlled than often portrayed. The granite core that shouldn't exist does exist. It rests in museum collections, its spiral grooves unchanged by time. It does not prove the existence of lost machines. It proves the existence of precision, and precision demands explanation grounded in material science, not assumption. The first crack in the official story is not a collapse but a hairline fracture where data and narrative misalign. That fracture invites closer measurement rather than louder claims. In 1883, Petrie brushed sand from a fragment of granite and saw not myth but mechanics. He saw uniform pitch where randomness was expected. He saw feed rates where abrasion alone was presumed. He saw in a simple cylindrical core evidence that ancient drilling practices were more sophisticated than a casual glance would suggest. The discovery did not change history overnight. It simply introduced a question that has yet to settle fully. How did a civilization armed with copper and sand produce spiral grooves in granite that look, by every measurable standard, mechanical? Granite does not care about stories. It responds only to force, pressure, and hardness. On the Mohs scale, which ranks minerals by their resistance to scratching, quartz sits at a 7. Granite, being largely composed of quartz, feldspar, and mica, inherits that resistance. Copper, by contrast, rests around 3. It is soft enough to bend under modest pressure, soft enough that a steel nail can scratch it without difficulty. This numerical disparity is not a matter of opinion or interpretation. It is measurable, repeatable, and indifferent to theory. When two materials meet, the harder one governs the exchange. A softer metal cannot meaningfully cut a harder crystal without assistance. That is the equation at the heart of the debate. Granite at 7, copper at 3. The official explanation has long been that copper tools were not the true cutting agents. Instead, quartz sand, also around 7 on the Mohs scale, served as the abrasive intermediary. The copper tube or saw acted merely as a holder, a vehicle to press sand slurry against stone while water carried the grains into the cutting interface. In principle, this makes sense. Abrasive machining remains a valid technique today. Modern waterjet cutters use garnet particles suspended in high-pressure streams to slice through steel. The hardness of the abrasive, not the carrier medium, performs the cutting. By analogy, ancient Egyptians could have used quartz sand to grind through granite. The problem is not theoretical possibility. The problem is behavior under measurement. Experimental archaeologists have spent decades attempting to reproduce Egyptian granite drilling using copper tubes, sand slurry, and manual rotation. The results are instructive. With sufficient time, sand can abrade granite. After hours of steady motion, a shallow groove forms. The process is slow and physically taxing. Copper tubes deform, requiring frequent reshaping. The sand distributes unevenly, sometimes biting aggressively, sometimes slipping without cutting. The resulting drill marks show variability. Groove depths fluctuate slightly along the circumference. Striations intersect at irregular angles. The rate of penetration changes as abrasive particles fracture or wash away. None of this invalidates abrasion as a method. It simply describes its natural signature. Abrasion leaves behind evidence of variability. Human motion, no matter how disciplined, contains micro-adjustments. Pressure fluctuates subtly with fatigue. The wrist shifts angle by fractions of a degree. The distribution of slurry changes as water evaporates or drips downward. These fluctuations accumulate in the stone. When examined under magnification, experimentally produced drill holes display a textured chaos consistent with this reality. In contrast, the spiral grooves documented on the Giza granite cores present a different character. Their spacing remains astonishingly consistent over multiple revolutions. The depth per turn appears uniform. The internal striations run parallel with minimal cross-hatching. The surface looks less like the product of distributed grit and more like the trace of a cutting edge advancing predictably. This distinction is subtle but critical. The abrasion theory explains how granite could be cut. It does not automatically explain why the groove spacing feels machined. To say something feels machined is not to claim advanced machinery. It is to recognize pattern regularity beyond what casual manual action typically produces. In machining terminology, feed rate refers to the distance a tool advances into material per revolution. When feed rate is constant, the resulting spiral exhibits consistent pitch. When feed rate varies, the pitch fluctuates accordingly. On the granite cores, the pitch does not drift. That constancy implies either extraordinary manual discipline maintained over extended rotations or some method of constraining vertical motion relative to rotation. The difference between effort and control lies here. Effort can generate force. It can grind and polish and carve. Control governs trajectory. Control determines whether each revolution advances the same distance as the one before it. In modern lathes, this relationship is enforced mechanically. A lead screw couples rotational movement to linear advancement, guaranteeing uniform pitch. Without such coupling, a human operator must manually regulate downward pressure while rotating the tool, an inherently less precise arrangement. It is important not to exaggerate. Ancient craftspeople were capable of astonishing precision. Repetition over generations refines technique. Weighted drill rigs could, in theory, maintain steady downward force while workers rotated the shaft. A simple frame suspending a stone weight atop a drill tube might approximate constant pressure. Yet constant pressure alone does not guarantee constant feed rate. The rate of penetration depends on the interaction between abrasive particles and crystal structure. Quartz grains fracture under load, altering cutting efficiency. Water flow redistributes abrasive concentration. Even under steady weight, penetration can accelerate or decelerate slightly as conditions change. These micro-variations should register in the groove geometry. On the Petrie cores, variation appears minimal. Modern profilometry scans show spiral ridges separated by nearly identical intervals along measurable lengths. The tolerance falls within fractions of a millimeter. Such uniformity suggests a process less vulnerable to stochastic drift than open slurry abrasion. Some researchers argue that the apparent regularity may result from overlapping passes of abrasive action, smoothing out irregularities over time. According to this view, prolonged grinding could average out fluctuations, producing the illusion of mechanical feed. However, averaging does not eliminate the initial pattern of irregular penetration. It tends to blur it. If abrasive action varied from revolution to revolution, the resulting surface would show blended textures rather than crisp, evenly spaced ridges. The cores instead display distinct helical tracks. The conversation therefore shifts from possibility to probability. Is it physically possible to drill granite with copper and sand? Yes. Is it probable that such a method would consistently produce uniform pitch across multiple cores without measurable drift? That question remains open. Engineers analyzing the cores focus less on etiology and more on material behavior. Granite is heterogeneous at microscopic levels. Quartz crystals intersect feldspar grains at varying orientations. As a drill advances, it encounters alternating resistance. Hard inclusions can deflect a soft tool slightly, altering trajectory. In experimental settings, this manifests as minor lateral wander and uneven groove walls. The Petrie cores, by contrast, exhibit relatively smooth interior surfaces, suggesting stable alignment throughout penetration. Stability implies guidance. Guidance implies constraint. Constraint does not necessarily mean advanced metal alloys. It could mean rigid framing, perhaps more elaborate than surviving evidence indicates. But the physical paradox persists because surviving copper tools displayed in museums do not show the wear patterns one might expect from sustained granite drilling at the implied feed rates. The wear would be severe. Copper edges would deform rapidly under pressure against quartz grains. Frequent reshaping would be necessary, interrupting the uniformity of motion. Each interruption would risk slight misalignment upon resumption. The spiral grooves, however, do not show abrupt transitions suggesting repeated tool removal and repositioning. Their continuity suggests uninterrupted rotational advancement. The difference between effort and control becomes clearer when one considers time. Effort accumulates slowly. It relies on endurance. Control, once established, enforces consistency automatically. If a system couples rotation and descent mechanically, each revolution advances the same increment regardless of operator fatigue. If a system relies purely on manual pressure, the operator must consciously regulate both torque and vertical force. Over extended drilling sessions, maintaining exact proportionality between rotation and descent becomes increasingly difficult. The granite cores appear to reflect proportionality rather than improvisation. This is not sensationalism, it is a matter of comparing patterns. The Mohs hardness contradiction frames the debate numerically, 7 versus 3. The abrasion explanation attempts to bridge that gap by inserting quartz sand as the true cutting medium. Experimental archaeology confirms that this bridge can carry weight, but perhaps not as efficiently or as uniformly as the cores imply. The mechanical appearance of the grooves challenges researchers to reconcile observable geometry with accepted tooling. Some scholars suggest that ancient Egyptians may have used harder materials than traditionally acknowledged, perhaps incorporating corundum or emery as abrasives. Corundum ranks at 9 on the Mohs scale and would significantly enhance cutting efficiency. However, evidence for systematic corundum use in Old Kingdom Egypt remains sparse. Even if such abrasives were employed, the question of feed control persists. Abrasive hardness addresses penetration rate. It does not inherently solve the problem of consistent pitch. Ultimately, the granite versus copper equation is not impossible in absolute terms. It is improbable in the specific configuration observed. Improbability is not proof of absence. It is an invitation to refine understanding. The physical paradox lies in reconciling measurable regularity with tools assumed to be irregular in performance. Granite, indifferent to narrative, preserves the history of its cutting. Its spiral grooves are data frozen in crystal. Copper tools may have played a role, perhaps in conjunction with abrasives and weighted rigs more sophisticated than often depicted. But the measurable uniformity of pitch and depth suggests that the ancient drilling process possessed a degree of control exceeding casual expectation. Establishing this paradox without sensationalism requires restraint. There is no need to invoke lost machines or forgotten civilizations. The paradox stands on its own in the numbers, 7 against 3, abrasion against feed, effort against control. The granite core does not accuse history of deception. It simply records geometry, and geometry, once measured, resists simplification. Beneath the desert plateau at Saqqara, in a network of dim corridors cut into limestone bedrock, sit objects that feel less like relics and more like industrial artifacts abandoned mid-project. The Serapeum of Saqqara houses a series of massive granite boxes, often described as sarcophagi, though their scale and precision exceed what the word usually implies. Each box weighs in the range of 60 to 70 tons, carved from single blocks of granite or diorite, materials chosen not for ease but for endurance. Their dimensions are monumental, yet their surfaces are not rough or symbolic. They are engineered. The exterior walls rise with sharp, clean edges. The lids, some weighing an additional 20 tons, sit atop the bases with tolerances that resist casual insertion of even a thin blade. These are not hollowed stones shaped quickly to house ritual remains. They are geometries executed at scale. When modern engineers bring straight edges and precision instruments into those underground chambers, the data begins to unsettle the romantic narrative. Measurements taken along the interior walls of several boxes indicate parallelism within fractions of a millimeter over spans exceeding 2 meters. In practical terms, that means opposing walls deviate from true parallel by amounts nearly imperceptible even with contemporary machining standards. The floors appear level within similar tolerances. Corners approach 90 degrees with a sharpness that defies the expectation of hand-driven chisels. Granite, dense with interlocking quartz crystals, resists fine finishing. Yet the interior surfaces of some serapeum boxes display a polish approaching reflectivity, smooth enough to produce faint mirrored images when illuminated directly. Achieving such finishes requires not only abrasion but control over flatness. Polishing a surface smooth does not guarantee it remains flat. Maintaining both simultaneously demands systematic refinement. The sealed nature of the chambers intensifies the question. These boxes were placed in underground corridors. Some slid into alcoves with little room for maneuvering. Once positioned and sealed with lids, their interiors were effectively hidden from view. If ritual alone were the objective, one might expect symbolic decoration, carved reliefs, inscriptions proclaiming devotion. Instead, the emphasis appears to have been on geometric perfection inside spaces that few, if any, would ever see again after sealing. The act of finishing the interior to such a high standard suggests that the precision itself mattered beyond aesthetics. It implies a value placed on flatness, squareness, and smoothness, independent of visibility. Transporting 70-ton monoliths into subterranean corridors presents its own logistical puzzle, but the transport question, while fascinating, is secondary to the machining question. The more immediate anomaly lies in how the interior cavities were hollowed so precisely. Removing tons of granite from a block while preserving parallel walls demands accurate reference surfaces. In modern workshops, machinists rely on surface plates, calipers, and alignment tools to maintain tolerances. In ancient Egypt, the toolkit as traditionally described includes copper chisels, stone pounders, and abrasive sand. Such tools can shape granite, but shaping differs from calibrating. To achieve walls parallel within fractions of a millimeter over multi-meter spans, one must measure repeatedly against a consistent standard. One of the boxes in the serapeum corridor offers a rare glimpse into process rather than product. This so-called unfinished box displays a miscut along one interior edge, a deviation where the surface plane shifts slightly, creating a visible step. The misalignment suggests a tool slipped or an error occurred mid-process. The box was left incomplete, its imperfection preserved. This detail is crucial because it confirms that the level of precision observed elsewhere was not accidental. It required deliberate effort. When the process faltered, the deviation was obvious enough to render the box unsuitable for whatever standard governed acceptance. The presence of a miscut demonstrates quality control. It reveals that craftsmen recognized error and halted production rather than disguising it with decoration. Examining the interior surfaces closely reveals subtle planar consistency. Straight edges placed along the walls show minimal light passing beneath, indicating flatness beyond what random abrasion typically yields. The polish appears layered as though coarse leveling preceded finer smoothing stages. Granite polishing traditionally involves progressively finer abrasives, each stage removing scratches from the previous one. Maintaining flatness throughout this sequence requires careful distribution of pressure. Uneven abrasion can introduce concavity or convexity. The serapeum interiors display remarkable resistance to such distortion. The question arises, why invest such precision in underground boxes? Some Egyptologists attribute the craftsmanship to reverence for sacred bulls associated with the Apis cult, suggesting that ritual significance justified extraordinary care. Ritual significance may indeed motivate effort, but it does not automatically generate technical method. Devotion explains why something is done. It does not explain how it is achieved. The how resides in technique, in control of tools against material. What complicates the narrative further is regression. The serapeum boxes are generally dated to the New Kingdom and later periods, yet similar levels of interior precision appear more prominently in earlier Old Kingdom contexts, such as certain granite elements in the Great Pyramid complex. As dynasties progressed, Architectural forms grew elaborate, temples expanded, ornamentation flourished. Yet the hyper-precise granite machining seen in these boxes did not proliferate proportionally. Later sarcophagi often exhibit decorative complexity but less extreme geometric tolerance. This pattern suggests that the capacity for such precision was not steadily increasing over time. Instead, it appears in concentrated bursts, then diminishes. Regression challenges the assumption of linear technological evolution. If a civilization develops a highly controlled stoneworking method, one expects refinement and dissemination. Instead, the serapeum boxes stand as isolated peaks. The skill appears, executed at monumental scale, then fades into more conventional craftsmanship. This does not imply loss of knowledge in a dramatic sense. It may indicate shifts in cultural priorities, resource allocation, or guild specialization. Yet the physical evidence remains. Few later works match the same combination of mass, flatness, and polish. Engineering analysis focuses on surface deviation. Modern granite surface plates used in laboratories are certified to flatness tolerances measured in microns. The serapeum interiors do not meet those modern standards, but they approach a level that demands explanation. Measuring equipment placed along the walls reveals deviations small enough to raise eyebrows among machinists accustomed to contemporary tools. Achieving such flatness manually is not impossible, but it requires systematic checking against reference surfaces. What reference surfaces did ancient craftsmen use? Limestone floors? Wooden straight edges? Granite master blocks? The archaeological record offers limited insight into calibration tools. The weight of the lids introduces another layer. Seating a multi-ton lid onto a base requires that mating surfaces align accurately. If surfaces are uneven, the lid rocks or leaves gaps. Several serapeum boxes show lid placement so snug that inserting even thin material between lid and base proves difficult. This suggests not only flatness but matching flatness between two independently finished surfaces. Achieving complementary flatness without precision measurement tools requires iterative testing and correction. The unfinished miscoat box reinforces the idea of controlled process. The deviation visible inside it appears as a step where one plane meets another at an unintended angle. The fact that this box was abandoned implies a standard threshold beyond which error was unacceptable. Such standards reflect awareness of tolerance limits. Craftsmen knew when flatness had been compromised. The regression question remains central. Why did subsequent dynasties, with access to similar or even expanded resources, not continue producing granite interiors of comparable tolerance regularly? One possibility is economic. The labor and time required to achieve such precision may have been prohibitive for routine production. Another possibility involves specialization. Perhaps a guild or group possessing unique technique operated during a particular era, and their method was not widely transmitted. Cultural shifts could deprioritize subterranean precision in favor of visible ornamentation. Regardless of motive, the serapeum boxes stand as data points in stone, 70 tons shaped with parallelism, measured in fractions of millimeters. Mirror-like finishes inside chambers, sealed from view. A miscut box revealing human fallibility within an otherwise disciplined process. And a historical arc in which such extreme geometric execution appears, then diminishes. The story told by these granite monoliths is not mystical, it is technical. It speaks of control exercised at scale, of craftsmen who understood flatness not as aesthetic flourish, but as measurable condition. The paradox lies not in their existence, but in their singularity. Precision beyond ritual appears, fully formed, then recedes, leaving behind corridors of stone that preserve the memory of skill without fully revealing the method that produced it. In the granite quarries of Aswan, south of the Nile's first cataract, the bedrock itself preserves a moment that never resolved. The unfinished obelisk lies half freed from the earth, a monolith still tethered to the stone from which it was intended to rise. Its mass would have exceeded 1,000 tons had it been completed. Longer than many city buses and heavy enough to strain any known lifting system attributed to the new kingdom. Yet it was never lifted. It remains anchored, surrounded by tool marks that transform the quarry floor into something resembling a halted production line. Unlike temples where surfaces were smoothed and ritualized, Aswan exposes process. Here the marks are raw, repetitive, and unapologetically functional. They record motion rather than myth. Walking along the trench cut around the obelisk's perimeter, the first impression is rhythm. The granite walls that frame the obelisk's sides are lined with shallow depressions, evenly spaced, forming a pattern of scalloped impressions. Each scoop curves into the next, creating a sequence that resembles the imprint of a massive rounded chisel or pounder applied in systematic progression. The spacing between these depressions is not chaotic. It follows a consistent interval, as though workers advanced along the stone in measured steps. This is not the random texture of exploratory hammering. It reads like a planned sequence, a path traced repeatedly with deliberate overlap. The trough cut along the base of the obelisk deepens the impression of organized effort. To detach a monolith from bedrock, workers carved a channel along its sides and beneath it, gradually isolating the form from the surrounding granite. That trough descends several feet, with walls that exhibit repeated curving cuts aligned in horizontal bands. The cuts appear layered, each band representing a pass at a particular depth. Rather than uneven gouges, the walls show a progression that suggests workers maintained consistent orientation of tools. The repeated curvature implies that the same type of instrument or motion was applied throughout the excavation. Traditional accounts describe stone pounders made of dolerite used to batter granite surfaces until fractures allowed removal. Dolerite balls have indeed been found in the quarry, lending credibility to the method. Yet when one examines the trough's interior closely, the marks appear less like chaotic fracturing and more like directed abrasion. The scalloped depressions align in ways that imply continuity of motion rather than isolated impacts. If pounders were used, they were applied with remarkable regularity. The surface does not display random shatter patterns typical of blunt force extraction. Instead, it resembles an organized grid of repeated strokes. Certain sections of the quarry floor and trench walls reveal another anomaly, patches of granite that appear altered in texture and sheen. These areas exhibit a slightly glassy appearance compared to the surrounding stone, as though exposed to elevated temperatures sufficient to modify surface minerals. Granite vitrification requires substantial heat. Whether these sections result from frictional heating due to intense abrasion, from fires set to weaken the rock, or from natural causes remains debated. However, their presence in proximity to systematic tool marks invites consideration of controlled heat application. If workers use fire to expand and fracture granite before pounding, localized heat alteration might occur. Yet the vitrified zones appear selective rather than widespread, suggesting directed exposure rather than accidental burning. The trench surrounding the obelisk narrows in places to a width that would challenge manual maneuvering. Workers had to operate within confined corridors, striking downward and inward to deepen the channel. Maintaining alignment in such spaces demands coordination. The trough does not wander. It follows the intended contour of the obelisk's sides with disciplined adherence. The edges of the monolith remain surprisingly straight, despite the roughness of the quarry context. This consistency indicates that reference lines were established before excavation progressed. Workers likely marked boundaries on the bedrock surface, then advanced inward while preserving those guides. The most dramatic feature of the unfinished obelisk is the crack that halted its liberation. A long fissure runs along its length, visible across the upper surface. At some point during cutting, stress within the granite manifested as a fracture, compromising the integrity of the monolith. Granite contains natural fault lines and inclusions. When shaping a mass of such scale, internal weaknesses can reveal themselves unpredictably. The crack effectively ended the project. Rather than attempt repair or reduction into smaller blocks, the obelisk was abandoned in situ. Its incomplete state preserves the cutting process in a way completed monuments cannot. That crack is more than geological misfortune. It indicates that workers pursued a one-piece extraction strategy. They intended to raise the obelisk intact. The trench around it demonstrates that systematic undercutting was underway. Had the method been improvisational, the fracture might have prompted adaptation. Instead, the work ceased entirely. This suggests that the cutting sequence depended on the monolith's structural continuity. Once compromised, the plan no longer functioned. Examining the scalloped marks more closely reveals variations in depth corresponding to different stages of excavation. Near the surface, the depressions are shallower, indicating initial passes that defined the perimeter. Deeper within the trench, the scallops intensify, reflecting sustained effort to isolate the obelisk's underside. The pattern does not degrade as depth increases. If anything, it becomes more regular, implying that as workers committed further to the project, their technique stabilized rather than deteriorated. This stability reinforces the impression of systematic cutting rather than opportunistic pounding. The quarry walls adjacent to the obelisk also display parallel channels carved into the bedrock, separate from the monolith itself. These channels align in consistent orientations, suggesting other extraction attempts nearby. When viewed collectively, the quarry resembles a workshop paused mid-operation, blocks partially separated, channels marked out, surfaces patterned with repetitive tool signatures. It feels less like an ancient ruin and more like a manufacturing site left abruptly. Experimental archaeology has attempted to replicate similar scalloped patterns using dolerite pounders. Results demonstrate that repeated hammering can indeed produce shallow depressions resembling those at Aswan. However, reproducing the depth and uniform spacing across extended surfaces proves labor-intensive. The Aswan trough extends tens of meters. Maintaining consistent depression spacing over such lengths would require either extraordinary discipline among workers or a guiding method that constrained movement. The impression left in granite reads almost like the feed pattern of a rotating cutter, though evidence for rotary machinery is absent. Still, the visual analogy persists because the spacing suggests rhythm beyond randomness. The vitrified sections complicate interpretation. Some geologists argue that these glossy patches could result from natural weathering or mineral concentration differences, yet their distribution within active cutting zones invites scrutiny. If friction between tool and stone generated localized heating, repeated strokes in the same area might elevate temperatures enough to alter surface appearance. Granite subjected to high-speed grinding can exhibit sheen changes. Whether ancient methods achieve such friction levels is uncertain. Nonetheless, the altered texture suggests energy concentration beyond casual pounding. Looking down into the trench at sunset, when shadows exaggerate surface relief, the scallop depressions form horizontal bands that resemble contour lines on a topographic map. The effect emphasizes continuity. Each band marks a level reached through repeated application of force. The granite did not fracture randomly. It yielded incrementally under patterned assault. The quarry preserves these increments like a ledger of labor. The unfinished obelisk also reveals planning at macro scale. Its sides were already partially shaped into the tapered form characteristic of erected obelisks. Workers did not simply outline a rectangular block. They carved facets that would eventually define the monument's final geometry. This indicates that shaping occurred before full detachment. The decision to sculpt while the stone remained anchored provided stability but required foresight. Any miscalculation in taper or alignment would propagate through the entire length. The crack terminated that risk before it matured. Around the obelisk's base, wedge holes appear in certain areas, though not extensively. These may have been intended to assist final separation. Their limited presence suggests that most of the detachment relied on trench undercutting rather than wedge-driven splitting. The systematic deepening of the trough indicates reliance on gradual isolation rather than explosive fracturing. Such gradualism aligns with the observed scalloped pattern. When modern visitors descend into the trench, the confined space amplifies sound. A single footstep echoes sharply, rebounding off granite walls. The acoustic response underscores the density of the material. Working within that echo chamber, ancient quarrymen would have experienced constant auditory feedback from their tools. Repetition would have been necessary to maintain rhythm and depth control. The consistent scalloping suggests that teams may have synchronized strikes, advancing along defined segments before moving to the next. The crack itself likely developed from internal stress distribution, as material was removed unevenly. Granite under tension can release strain unpredictably. Once the fissure appeared, the monolith's structural viability collapsed. Transporting a cracked obelisk of such scale would risk catastrophic failure. Abandonment preserved the evidence of ambition exceeding geology's tolerance. Viewed holistically, the Aswan quarry reads like an interrupted industrial endeavor. Deep troughs with layered scallops, selective vitrified patches hinting at concentrated energy. A massive form partially sculpted yet inseparable from its bedrock origin. Evidence of systematic cutting patterns extending beyond a single monument. The absence of ornament or inscription emphasizes function. This was not ceremonial space but production space. The unfinished obelisk therefore offers more than a failed monument. It provides a snapshot of process frozen in granite. The regularity of tool marks implies method. The vitrified sections suggest interaction between force and heat. The decisive crack illustrates dependence on structural continuity, and the broader quarry environment reinforces the impression of organized extraction rather than haphazard quarrying. Egypt in this moment does not appear as a land of mystical builders chiseling by intuition. It resembles an industrial site where material science met ambition, where precision and mass coexisted, and where one fracture halted a workflow that had been advancing with disciplined repetition. When modern researchers brought laser profilometers to the granite cores extracted from Giza, the conversation shifted from impression to measurement. What had once been described in notebooks as regular or even could now be mapped in microns. A rotating laser beam traced each spiral groove along the cylindrical fragments, capturing depth, spacing, and angular deviation at thousands of points per second. The resulting data sets were not sketches or subjective interpretations. They were dense clouds of numbers defining the surface geometry in 3 dimensions. And what emerged from those scans was not randomness worn smooth by time, but repetition precise enough to suggest rule rather than accident. Multiple cores, recovered from different drill holes across the plateau, were scanned independently. Each displayed a helical groove wrapping around the cylinder's exterior, the trace left behind when a tubular drill advances into stone. The crucial observation was not merely that the grooves spiraled, but that their pitch, the distance the drill advanced per full revolution, remained remarkably consistent along the length of each core. In machining terms, pitch corresponds directly to feed rate relative to rotational speed. If rotation increases while downward pressure remains stable, the pitch changes. If pressure fluctuates, the groove spacing varies. On these ancient cores, however, the pitch remained nearly uniform from top to bottom, deviating only within narrow tolerances measurable in fractions of a millimeter. To understand why this matters, consider what constant feed rate means in modern machining. When a drill bit penetrates material, 2 motions combine, rotation and linear advance. The feed rate describes how far the tool moves forward with each revolution. In controlled systems, such as computer numerical control machines, feed rate is regulated mechanically or digitally to maintain uniform cutting conditions. Deviations produce chatter marks, inconsistent groove spacing, or irregular surface finish. Human hands alone can rotate and push a tool, but sustaining identical advancement per revolution across extended depth is extremely difficult. Variations in muscle fatigue, resistance changes within the material, and micro-adjustments inevitably introduce irregularity. The laser scans revealed something unexpected. Along several cores, the feed per revolution appeared constant enough to imply steady coordination between rotational and axial movement. When the spiral was digitally unwrapped into a straight line for analysis, its slope, the geometric representation of pitch, remained linear rather than wavering. This does not automatically prove mechanical drilling in the modern sense. However, it indicates that the process governing motion was regulated with a degree of stability uncommon in purely manual abrasion. Equally significant was cross-artifact comparison. When engineers overlaid scan data from separate cores, extracted from different locations and potentially different time periods, the pitch values aligned closely. The grooves did not merely resemble each other visually. Their measured advance rates clustered around similar numeric ranges. In manufacturing, such clustering suggests calibration to a standard. It implies that whoever executed the drilling operated within constraints that preserved specific motion ratios. Consistency across multiple artifacts strengthens the case that the phenomenon reflects system behavior rather than individual improvisation. In machining, constant feed rate serves several purposes. It maintains predictable cutting forces, reduces tool wear, and ensures surface finish quality. When feed fluctuates, the tool can bite too aggressively or skate ineffectively, producing uneven marks. Granite is heterogeneous, containing quartz crystals embedded in feldspar and mica. Resistance changes as the tool encounters different mineral inclusions. A manual operator pushing against such variability would naturally adjust pressure, altering groove spacing. Yet the spiral grooves appear indifferent to these variations, advancing with near metronomic steadiness. The engineering lens does not demand that ancient builders possessed electric motors or hardened steel bits. It asks instead whether the observed consistency reflects deliberate process control. Process control means the method itself constrained variables, whether through weighted systems, guided frames, or coordinated teams maintaining synchronized motion. A bow drill rotated by hand, for example, introduces oscillatory motion. Each stroke accelerates and decelerates the tool. Maintaining identical forward advance during such cyclic movement would require extraordinary coordination. By contrast, a suspended weight applying steady downward force while rotation remains continuous would naturally stabilize feed rate. Laser profilometry also revealed depth uniformity within individual grooves. The bottom of the spiral trench did not oscillate dramatically in depth. Instead, it maintained consistent penetration relative to the surface. In machining, this indicates stable engagement between tool and material. If pressure spikes or drops, depth fluctuates. The measured steadiness suggests that the downward force applied during drilling was neither erratic nor reactive. It was maintained within a narrow band. Critics argue that abrasion with sand slurry can produce spiral marks as grit accumulates unevenly. However, abrasion without rotational constraint typically yields irregular patterns. The quartz grains embedded in granite resist uniform cutting. If grit distribution shifts, the groove's width and depth vary. The scan data shows limited lateral wandering. The groove tracks a coherent helical path with minimal drift. Such coherence implies that the cutting interface remains stable relative to the stone's axis. Consistency matters more than speed because it reveals control rather than brute effort. Even if ancient drilling progressed slowly, maintaining constant feed would require coordination between rotation and advance. Speed alone could be achieved through patience. Control demands structure. In engineering diagnostics, variability often exposes weakness. A surface riddled with inconsistent marks suggests ad hoc adjustment. A surface defined by uniform spacing indicates a process insulated from momentary fluctuation. Some researchers quantified groove pitch as approximately 1/10 of an inch per revolution on certain cores. Whether this exact value remains debated, the broader point stands. Measurable advancement per revolution occurred, and it did not collapse into chaos along the core's length. That advancement corresponds to material removal rates that surprised early engineers studying the fragments. Even if cutting occurred over extended durations, the groove geometry reflects steady-state conditions rather than cumulative error. Another aspect revealed by scanning was angular fidelity. The helix angle, the angle between the spiral and the core's longitudinal axis, remained consistent. Variations in helix angle correspond to shifts in feed rate relative to rotational speed. A wandering helix angle would suggest uneven push or inconsistent turning. Instead, the cores exhibited tight, angular clustering. This clustering reinforces the impression that rotation and advance were linked in a predictable ratio. In modern manufacturing, precision serves as a signature of system rather than improvisation. When parts produced in different batches share dimensional uniformity, engineers infer the presence of calibrated tools. When tolerance stacking remains minimal across multiple pieces, it indicates oversight beyond individual intuition. The granite cores reflect such tolerance behavior. They do not merely show that drilling occurred. They show that drilling occurred within boundaries that limited deviation. The engineering perspective doesn't negate traditional methods outright. It reframes the inquiry around mechanism stability. Could teams of workers rotating a drill via ropes and applying weighted downward force achieve such stability? Possibly. Could guide frames carved into stone constrain motion? Conceivably. What matters is not the specific hardware, but the evidence of process governance. The spiral pattern becomes less a curiosity and more a data stream pointing toward regulation. The distinction between improvisation and system lies in repeatability. An improvised action may succeed once. A system reproduces outcome across instances. The identical pitch observed across multiple cores hints at reproducibility. Reproducibility implies instruction, whether encoded in tools or training. It means that drilling followed rules, not solely muscle memory. Laser scans, by stripping away interpretive bias, illuminated geometry embedded in stone. They transformed anecdotal observations into measurable curves. Engineers reading those curves recognize patterns familiar from workshops rather than quarries. Constant feed rate, stable helix angle, consistent groove depth. These are hallmarks of controlled engagement between tool and material. The spiral pattern therefore functions as evidence of process control. It does not specify the machine, nor does it demand futuristic devices. It identifies stability and motion. Granite cores from Giza exhibit geometry that aligns with principles governing regulated cutting operations. The regularity across artifacts strengthens the inference that the builders employed methods capable of constraining variables over time. Precision here becomes more than aesthetic achievement. It acts as diagnostic marker. In complex systems, precision signals feedback loops preventing drift. Whether that feedback derived from mechanical guidance, weight-driven pressure, or collective synchronization, the outcome remains visible in the stone. Each spiral groove encodes a ratio between rotation and advance, preserved for millennia. When data replaces drama, the conversation shifts. Instead of marveling at mystery, one evaluates tolerance bands and angular consistency. The granite cores become case studies in ancient material interaction. Their spiral patterns testify not merely to effort, but to controlled procedure. In engineering terms, they reveal that someone at some time managed rotational motion and linear advance with enough discipline to leave behind geometry indistinguishable in principle from regulated machining processes. Inside the king's chamber of the Great Pyramid, sound behaves in ways that resist casual description. Visitors who speak softly notice their voices deepen and stretch. A single sustained note does not simply rebound from the granite walls. It thickens, folds, and lingers, as though the air itself prefers certain tones over others. When modern acoustic researchers brought calibrated microphones and frequency generators into that chamber, they were not searching for mysticism. They were measuring reverberation time, decay curves, and modal distribution. What they found was a dominant resonance clustering near 438 Hertz, a frequency strikingly close to the modern musical A used for tuning orchestras. The number itself is not magical, but the consistency of reinforcement around that band has prompted careful analysis. Resonance occurs when a space reinforces specific frequencies due to its dimensions and material boundaries. Every enclosed volume has natural modes determined by length, width, and height. In a simple rectangular room, these modes can be calculated using established acoustic equations. The king's chamber, constructed from massive granite blocks, presents a rigid boundary condition that reflects sound efficiently. Granite's density and low porosity limit energy absorption, allowing standing waves to form more readily than in softer materials. When researchers emitted frequency sweeps from 50 to 1,000 Hertz, they observed amplification spikes corresponding to modal frequencies predicted by the chamber's geometry. Among these, the region around 438 Hertz produced pronounced reinforcement. Standing waves arise when incident and reflected waves align in phase, creating nodes and antinodes within the space. At nodes, air pressure fluctuation is minimal. At antinodes, it intensifies. In the king's chamber, pressure mapping revealed stable antinodes forming near the chamber's center and along specific wall intersections when stimulated near the resonant band. A sustained tone at that frequency did not dissipate quickly. Instead, it maintained amplitude longer than adjacent frequencies, indicating low damping and efficient reinforcement. The effect is measurable. Decay time at the resonant frequency exceeded that of neighboring frequencies under identical stimulus conditions. What distinguishes this phenomenon from ordinary echo is alignment. Echo implies discrete reflections perceived as repetition. In the chamber, certain tones merge with the room rather than bounce distinctly. The reflected wave returns in phase with the incoming one, amplifying rather than duplicating it. Listeners report that a hum at the resonant frequency feels embodied rather than external, as if the vibration settles into the chest cavity. From an acoustic standpoint, this sensation results from constructive interference and prolonged sustain. The geometry of the king's chamber contributes directly to this behavior. Its dimensions approximate integer ratios that align with harmonic relationships. While minor deviations exist due to erosion and reconstruction uncertainties, the chamber's length, width, and height create modal frequencies that cluster in musically coherent intervals. Engineers modeling the chamber digitally have shown that altering even one dimension by several centimeters shifts the dominant resonant frequency significantly. The existing geometry appears tuned to support low-frequency reinforcement within a narrow band. Granite as a material further influences acoustic performance. Rich in quartz, it reflects sound with minimal internal absorption. When excited by vibration, quartz-bearing stone can exhibit piezoelectric response, though the magnitude within bulk granite remains small. Nevertheless, mechanical stress propagates efficiently through such dense crystalline matrices. When a standing wave establishes itself within the chamber, the walls themselves vibrate microscopically. Laser vibrometry has detected minute surface oscillations synchronized with acoustic input at resonant frequencies. These oscillations remain within safe structural limits but confirm that the chamber participates physically in the acoustic field. The 438 Hz figure does not imply intentional alignment with modern tuning standards, which themselves have varied historically. What matters is that the chamber reinforces a specific band with measurable stability. When researchers introduced tuning forks calibrated slightly above or below this frequency, the reinforcement diminished. Only within a narrow tolerance did the amplitude sustain strongly. This selectivity suggests that the chamber's dimensions create a filter effect, privileging certain wavelengths. Standing waves within the chamber form predictable spatial patterns. When acoustic pressure maps are visualized, contour lines reveal symmetrical distributions consistent with axial modes. At the center of the chamber, a listener positioned at an antinode experiences intensified vibration. At nodal lines, sound appears diminished. This spatial structuring is not random. It corresponds directly to the chamber's rectangular geometry and reflective boundaries. Temple architecture throughout ancient Egypt demonstrates awareness of acoustic consequence. Hypostyle halls with rows of columns create diffusive scattering, preventing harsh echoes while sustaining chant. Narrow corridors funnel sound longitudinally, enhancing procession acoustics. Domed ceilings and vaulted chambers in later periods modulate reverberation for ritual recitation. These design choices indicate sensitivity to how sound behaves within built environments. Whether this sensitivity arose from experimentation or tradition, the results reveal deliberate shaping of auditory experience. In the king's chamber, the scale and rigidity amplify this shaping. The chamber is not adorned with reliefs or plaster that might dampen vibration. Its surfaces are smooth and massive. When chant or sustained tone occurs within it, the resulting field becomes immersive. Engineers analyzing impulse responses have noted that low-frequency components dominate the decay profile, indicating that the chamber favors deeper tonal content. High frequencies dissipate more rapidly, leaving a lingering bass resonance. Was sound structural rather than symbolic? This question reframes interpretation. If architects prioritized acoustic reinforcement, then chant and tone were not mere decoration layered onto architecture. They were integral to its function. Sound could have been used to test alignment during construction, to signal structural integrity, or to calibrate chamber dimensions. A mason striking granite blocks might listen for consistent pitch to confirm uniform density. Ritual specialists chanting within the chamber might have recognized how certain tones activated the space, reinforcing the belief that sound and stone interacted meaningfully. Acoustic anomalies extend beyond the king's chamber. Subterranean passages beneath the pyramid exhibit narrowband resonances associated with their elongated shapes. The so-called Queen's Chamber displays different modal distributions due to its sloped ceiling. Measurements show that its resonant frequencies diverge from those of the King's Chamber, suggesting intentional variation in acoustic character between spaces. Whether these differences reflect design goals or structural necessity remains debated, but the measurable distinction underscores the importance of geometry in shaping sound. Harmonic reinforcement occurs when fundamental frequencies align with integer multiples of spatial modes. In the King's Chamber, certain overtones of the dominant resonance coincide with secondary modes, creating layered reinforcement. This harmonic stacking enhances perceived richness of tone. Modern concert halls exploit similar principles to enrich musical performance. The difference lies in scale and purpose. The pyramid chamber lacks seating or stage. Its acoustic properties operate within a confined ritual space, rather than a public auditorium. Researchers employing spectrum analyzers have documented that the resonant peak near 438 Hz remains stable across environmental conditions within the chamber, though minor shifts occur with temperature changes. Air density influences wavelength, and thus modal frequency, but the granite boundaries maintain overall stability. This robustness indicates that the chamber's geometry exerts primary control over resonance rather than transient environmental variables. Some scholars caution against overinterpretation. Any rectangular stone room will exhibit resonances predictable by physics. The presence of a resonant frequency does not necessarily prove intentional tuning. Yet the strength and narrow-band nature of the reinforcement, combined with the chamber's precision construction, invite consideration of whether acoustics factored into design decisions. Ancient builders demonstrated capacity for astronomical alignment and geometric rigor. Extending that rigor to acoustic awareness is not implausible. Sound aligning instead of echoing alters human perception. In spaces where reflection is diffuse, speech remains intelligible but does not envelop. In the King's Chamber, alignment at resonant frequencies produces immersion. Participants in acoustic experiments report that sustained tones feel amplified internally. The phenomenon arises from pressure nodes interacting with the human body, whose cavities also resonate at low frequencies. The result is a coupling between chamber mode and physiological response. Temple rituals often centered on vocalization. Chant stabilizes breathing and enforces rhythmic unity among participants. If certain tones activated chamber resonance, ritual leaders might have selected pitch ranges intuitively aligned with architectural response. Over generations, such practices could solidify into tradition without explicit mathematical articulation. Sound would become structural not in the sense of supporting weight, but in shaping experiential stability within the sacred environment. Granite's mass also influences vibrational persistence. When excited at resonance, the walls store mechanical energy briefly before releasing it back into the air. This feedback loop extends sustain. Laser interferometry measurements have captured nanometer-scale oscillations on granite surfaces synchronized with acoustic excitation. Though minute, these oscillations confirm mechanical participation of the structure in the sound field. The idea that sound could play a structural role extends into engineering domains. Vibrational analysis today assesses building integrity by measuring modal frequencies. Changes in resonance can indicate cracks or stress shifts. Ancient builders lacking electronic sensors might have used auditory cues as diagnostics. A chamber that rang consistently at a specific tone would signal alignment. Deviations might suggest structural irregularities. Acoustic anomalies therefore shift attention from cutting stone to energizing it. The King's Chamber demonstrates that geometry and material combine to produce selective reinforcement. Whether this outcome was incidental or intentional remains debated, but the measurable data confirm that sound within the chamber behaves differently than in ordinary stone rooms of similar size. The resonance near 438 Hz persists as a reproducible feature under controlled testing. Temple architecture across Egypt reflects nuanced engagement with acoustics. From column spacing to ceiling height, spatial design influenced auditory character. In the pyramid, this engagement reaches extreme refinement. Sound does not merely inhabit the chamber, it interacts with it. standing waves stabilize, harmonics reinforce, and certain frequencies align seamlessly with spatial modes. The resulting acoustic environment suggests that vibration formed part of the chamber's experiential core. The transition from cutting to vibration reframes the narrative. Precision in carving granite established structural integrity. Precision in geometry established acoustic identity. Together they imply that ancient builders understood more than static form. They manipulated dynamic interaction between matter and motion. In the king's chamber, stone that sings is not metaphor but measurable phenomenon, captured in decay, curves, and frequency spectra. Whether interpreted as ritual amplification or architectural consequence, the acoustic anomalies stand as data points in the broader investigation of how geometry, material, and vibration intersected within ancient construction. Beneath the limestone crust of the Giza plateau, water moves quietly through fractures carved by geological time. It does not rush like a river. It seeps, presses, collects, and redistributes itself according to gradients invisible from the desert surface. Modern hydrogeological surveys have confirmed that groundwater exists below the pyramids, flowing through porous layers of Mokattam limestone and accumulating in pockets where impermeable strata trap it temporarily before releasing it onward. The plateau is not a dry pedestal suspended in isolation. It rests above a slow hydraulic system shaped by the Nile's fluctuations and regional aquifers. This subterranean motion rarely enters discussions of pyramid engineering, yet it forms part of the environmental matrix in which the monuments stand. Groundwater beneath Giza has been mapped using boreholes, resistivity imaging, and seismic profiling. These techniques reveal variations in moisture content and density below the plateau, indicating channels where water percolates more freely. Seasonal changes in the Nile historically influenced groundwater levels, especially before modern dam construction regulated the river's flow. When the river rose during inundation, subsurface pressure increased. When it fell, pressure subsided. Such oscillation creates subtle but measurable stress cycles in overlying rock. The pyramids themselves extend partially into bedrock. The Great Pyramid's foundation integrates carved limestone from the plateau, leveling the natural outcrop into a platform. Beneath this platform lie voids and cavities, including the subterranean chamber, carved directly into the limestone core. This chamber sits well below the base level of the pyramid and connects to descending passages that approach the water table. Though currently dry, geological evidence suggests that groundwater levels may have fluctuated closer to these lower structures in antiquity. Hydraulic pulse theories propose that variations in groundwater pressure could interact with stone structures above. When water moves through confined fractures, it generates pressure waves. These waves propagate through rock as mechanical vibrations. The magnitude of such vibrations depends on flow rate, channel geometry, and confinement. In modern geophysics, similar processes are observed in karst systems where subterranean water movement produces low-frequency tremors detectable by sensitive instruments. The plateau's limestone composition allows for water transport through microfractures, creating potential pathways for pressure transmission. Pressure interacting with stone introduces dynamic loading conditions. While the pyramids are massive and stable under static weight, periodic subsurface pressure changes could induce minute oscillations. Granite chambers within the Great Pyramid, particularly the King's Chamber, constructed of Aswan granite, rest above limestone blocks. Granite's mechanical properties differ significantly from limestone's. It is denser, stiffer, and rich in quartz. When stress waves propagate upward from subsurface hydraulic activity, the contrast in material properties affects how those waves reflect and refract. Subterranean chambers amplify this complexity. The descending passage and subterranean chamber create void spaces within the limestone mass. Voids alter stress distribution, focusing or diffusing pressure waves depending on geometry. In engineering, cavities can act as resonators when excited by external forces. If groundwater pulses produced low-frequency mechanical input, these cavities might respond selectively based on their dimensions. Though the energy involved would be small relative to structural capacity, the interaction between void, stone, and pressure merits examination. The Osirian at Abydos offers a parallel case where water and stone intersect visibly. This subterranean structure, located behind the temple of Seti I, lies below ground level and contains massive granite blocks arranged around a central basin. Even today, water accumulates within its chamber, fed by groundwater seepage. The Osirian's floor and channels guide water movement through a deliberate layout of basins and troughs. Its granite walls bear marks of careful cutting, similar to those seen in earlier Egyptian stonework. Hydrological studies at Abydos have documented continuous water presence within the Osirian, suggesting stable groundwater interaction. The structure's geometry includes channels that appear designed to manage water flow rather than exclude it. When seasonal rises occur, water levels increase predictably within the basin, then recede gradually. This cyclical filling and draining introduce mechanical interaction between water mass and stone enclosure. Water exerts hydrostatic pressure on chamber walls, and flow through channels generates microvibrations detectable with modern equipment. Pressure plus stone plus resonance forms the core of hydraulic pulse hypotheses. If groundwater movement beneath monumental structures generated periodic stress waves, and if those structures included cavities tuned to specific frequencies, then mechanical coupling between subsurface motion and architectural geometry becomes conceivable. This does not require high energy output. Even low amplitude oscillations can produce measurable resonance if structural modes align with excitation frequency. At Giza, some researchers have measured ambient microtremors using seismographs placed within pyramid chambers. These instruments detect constant background vibrations resulting from distant seismic activity, wind, and anthropogenic noise. In certain analyses, narrow frequency bands appear more pronounced within interior chambers than outside, suggesting structural filtering. Whether groundwater contributes meaningfully to these patterns remains debated, but the presence of natural mechanical input beneath the plateau is established. The limestone plateau functions as a porous medium. Water infiltrates through rainfall and historical Nile overflow, then migrates downward until encountering denser layers. During migration, pressure gradients develop. When water encounters constrictions, it accelerates locally. Increased over time, such pressure variations may create periodic loading cycles in the overlying rock mass. In large stone structures integrated with bedrock, these cycles translate into distributed stress fluctuations. Granite's response to stress includes elastic deformation and, due to its quartz content, minute piezoelectric effects. While the scale of charge generation in bulk granite is small, mechanical vibration remains real. If groundwater-induced tremors interacted with granite chambers, tuned to specific modal frequencies, amplification through resonance could occur. This amplification would not generate large-scale energy but could produce persistent low-frequency vibration within confined spaces. Hydraulic pulse theories often extend to speculation about energy generation, yet the data more cautiously indicate interaction rather than production. Water beneath the plateau provides environmental input. Stone above provides structural response. The coupling between them depends on geometry, material contrast, and excitation frequency. In engineering contexts, similar interactions are exploited intentionally in hydraulic turbines and resonance-based sensing devices. The question at Giza is whether ancient builders anticipated such interaction or simply built within an environment that naturally produced it. The Osirian strengthens the environmental argument by demonstrating architectural accommodation of water rather than avoidance. Its channels and basins suggest awareness of groundwater presence. Unlike the pyramids, whose interiors remain dry, the Osirian integrates water into its spatial logic. This integration implies that ancient architects understood groundwater behavior sufficiently to incorporate it into design decisions. Subterranean chambers beneath the Great Pyramid, particularly the unfinished subterranean chamber, present rough surfaces and incomplete geometry compared to the finished granite rooms above. Some researchers suggest that its location relative to groundwater levels, others view it as an experimental stage in the pyramid's design evolution. Regardless, its depth situates it near zones where hydraulic pressure fluctuations would be strongest. Environmental components thus become active rather than passive. Groundwater is not merely a background condition, it introduces mechanical variables. When combined with massive stone structures, these variables can create complex dynamic systems. Modern structural engineers consider soil-structure interaction crucial in large foundations. The pyramids represent extreme cases of such interaction due to their integration with bedrock. The Nile's historical flood cycle further contextualizes this system. Before modern regulation, annual inundation raised water tables across the region. Increased groundwater pressure during flood season could alter stress distribution beneath the plateau. Even if changes were gradual, cumulative effects over centuries might influence subsurface cavities and structural behavior. Though the pyramids have withstood millennia without visible hydraulic damage, subtle dynamic interaction remains plausible. Hydraulic pulse hypotheses do not claim that pyramids functioned as pumps or power plants in a conventional sense. Rather, they posit that environmental energy, mechanical and gravitational, interacted continuously with the structures. In such a view, the monuments become part of a coupled earth-water-stone system. Pressure changes propagate upward, structural modes respond, resonance may amplify specific frequencies while dampening others. In Abydos, water channels within the Osirian produce audible and tactile changes when flow increases. Visitors report slight temperature differences near active seepage zones. Measurements confirm modest thermal variation where water contacts stone. Thermal gradients can induce expansion and contraction cycles, adding another dimension of environmental stress. Combined with hydraulic pressure, these cycles contribute to the dynamic character of subterranean architecture. Introducing environment as active component reframes interpretation. Rather than viewing monuments as isolated artifacts, they become nodes within geological and hydrological networks. Groundwater flow beneath Giza, subterranean chambers carved into limestone, and granite structures resting above all participate in a shared physical system. Pressure interacting with stone produces motion, however subtle. Motion interacting with geometry produces resonance, however faint. The evidence does not demand that ancient builders harnessed groundwater deliberately for technological ends. It demonstrates that environmental forces were present and measurable. Whether intentionally incorporated or simply accommodated, water beneath the plateau constitutes a dynamic factor. When considering acoustic anomalies and structural precision together, groundwater adds a third variable: pressure input. Stone that sings and stone that cuts precisely may share a common foundation in environmental interaction. Granite chambers amplify sound. Limestone foundations transmit pressure. Water introduces cyclic stress. Together they form a complex interplay between material and motion. The plateau is not inert. It breathes slowly through aquifers and fractures. The monuments above respond mechanically to that breath. In engineering analysis, systems are rarely static. Foundations interact with soil. Structures respond to wind and seismic input. Applying similar thinking to ancient monuments shifts emphasis from isolated craftsmanship to integrated environment. Water beneath Giza and within the Osirion at Abydos illustrates that ancient builders worked in landscapes shaped by hidden motion. Whether consciously or not, their architecture stands within a field of pressure and resonance that continues to operate today. Granite is not a uniform substance but a crystalline composite forged under immense geological pressure. Within its interlocking matrix of feldspar and mica lies quartz, a mineral whose atomic lattice carries a well-documented physical property: piezoelectricity. When quartz crystals are mechanically stressed, compressed, stretched, or vibrated, they generate a small electrical potential across specific crystallographic axes. This phenomenon was first formally described in the 19th century, long after the pyramids were built, yet the principle itself is timeless. It is not a theory but a measurable behavior observed in laboratories worldwide. In small engineered devices, quartz transforms mechanical pressure into electrical signal with remarkable stability. The question relevant to ancient granite construction is not whether quartz produces charge, but whether the scale and context of massive granite blocks could yield measurable micropotentials under natural stress. Quartz exists in granite as dispersed crystals, often irregularly oriented. In a watch, a single crystal is cut along precise axes to maximize piezoelectric output. In granite, the quartz grains are not aligned intentionally, and their orientations vary. This randomness reduces net charge generation because adjacent crystals may produce opposing polarities when stressed. However, piezoelectricity does not vanish simply because orientation is disordered. Localized stress can still induce localized potentials, even if global output remains small. In engineering terms, bulk granite is not an optimized piezoelectric transducer, but it is not electrically inert. Mechanical stress in granite arises from multiple sources. Static load from overlying stone exerts compressive force. Thermal expansion and contraction introduce cyclic strain as temperatures fluctuate between day and night. Vibrational energy from wind, seismic activity, or acoustic resonance propagates through the crystalline lattice. Each of these stresses deforms quartz grains microscopically. In a laboratory, similar deformation applied to a quartz sample produces measurable voltage in the millivolt range. The magnitude depends on strain amplitude, crystal orientation, and surface area. Modern microphones exploit piezoelectric materials to convert sound pressure into electrical signal. When acoustic waves strike a piezoelectric diaphragm, mechanical displacement generates voltage corresponding to pressure variations. Quartz watches use precisely cut crystals that oscillate at stable frequencies when energized electrically. The reverse piezoelectric effect causes mechanical vibration in response to applied voltage. These technologies demonstrate the bidirectional relationship between mechanical stress and electrical potential. They do not imply that granite blocks function as microphones or oscillators by default, but they establish a material precedent. The granite used in the King's Chamber and other Old Kingdom structures originates from Aswan, known for high quartz content. Petrographic analysis shows quartz fractions significant enough to influence mechanical properties. Under compressive load, such granite exhibits elastic behavior within defined limits. Elastic deformation, though minute, is sufficient to activate piezoelectric response at microscales. The resulting charge dissipates rapidly unless collected by conductive pathways. In natural settings, surface charge may redistribute across the stone or leak into surrounding material. Could massive granite blocks produce microcharge? In principle, yes, if mechanical stress changes occur. The scale of the block increases the total volume of quartz under strain. However, net electrical output depends on orientation coherence. Random grain orientation leads to partial cancellation of generated potentials. Still, localized charge pockets may form along grain boundaries. Sensitive electrometers placed on stressed granite surfaces have recorded small, transient potentials under laboratory compression. These values are modest and decay quickly as equilibrium restores. Granite's electrical conductivity is low, but non-zero. It behaves as a poor conductor relative to metals, yet it permits limited charge mobility, especially when moisture is present along microfractures. Limestone, by contrast, generally exhibits higher resistivity and lower piezoelectric contribution because it lacks significant quartz content. In composite systems where granite interfaces with limestone, differences in conductivity and dielectric constant create potential for differential charge distribution. This contrast parallels modern capacitor design, where materials of differing electrical properties interact under field influence. The Great Pyramid combines granite chambers encased within limestone mass. Granite beams form the roof of the King's Chamber, while limestone blocks dominate the bulk of the structure. If mechanical stress induces micropotentials within granite, the surrounding limestone may act as an insulating medium, limiting rapid dissipation. However, environmental factors such as humidity, temperature, and contact surfaces influence leakage paths. Any generated charge would be transient unless sustained by repeated stress cycles. Mechanical vibration within the King's Chamber, documented through acoustic studies, introduces dynamic strain into granite blocks. Standing waves at resonant frequencies cause periodic compression and rarefaction within the chamber air, transferring minute pressure fluctuations to stone surfaces. The amplitude of such fluctuations is small compared to structural loads, but sufficient to induce elastic strain. The piezoelectric coefficient of quartz defines the relationship between applied stress and generated electric displacement. In bulk granite, effective coefficients are reduced by grain randomness, yet non-zero response remains plausible. Experimental setups replicating these conditions involve applying controlled vibration to granite slabs, instrumented with electrodes. Results show transient voltage spikes correlated with vibrational input, typically in microvolt to millivolt ranges. These values are far below levels required for power generation, but confirm material responsiveness. Scaling up to monolithic blocks increases total quartz volume, potentially increasing cumulative microcharge generation. However, scaling also increases cancellation effects unless stress distribution is coherent. Temperature cycles provide another stress mechanism. Granite expands and contracts with thermal variation. Differential expansion between quartz and feldspar components introduces internal strain. During cooling at night, contraction exerts tensile stress on certain grains. Piezoelectric response accompanies such deformation. Measurements in geological contexts have detected natural electric potentials associated with rock stress prior to seismic events, known as seismoelectric effects. Though these phenomena involve large-scale tectonic strain, they demonstrate that rock under stress can generate measurable electric fields. Granite conductor versus limestone insulator presents an intriguing juxtaposition. While neither material rivals metallic conductivity, their relative properties differ. Granite's quartz inclusions confer localized piezoelectric sensitivity. Limestone's calcite composition lacks similar behavior and tends to resist charge propagation. In a composite structure, differential electrical behavior may create minor field gradients. The magnitude of such gradients remains small, yet their existence underscores that stone assemblies are not electrically neutral in dynamic environments. Material science approaches this topic without invoking speculative energy devices. The relevant question concerns scale and interaction. If groundwater beneath the plateau introduces periodic stress waves, and if acoustic resonance within chambers induces vibration, then granite blocks experience dynamic strain. Each strain cycle potentially produces microcharge within quartz grains. Whether this charge accumulates meaningfully depends on boundary conditions. In open air, charges dissipate rapidly. Within confined chambers insulated by limestone, decay rates may differ slightly. Modern instrumentation can detect electric potentials in stressed rock using high-impedance probes. Field experiments near fault lines reveal transient electric signals preceding earthquakes, attributed partly to piezoelectric and electrokinetic mechanisms. The amplitudes recorded in such contexts are low but measurable over large volumes. By analogy, granite blocks under pyramid load experience constant compressive stress. However, static compression alone does not produce sustained current. Only changes in stress generate transient potential. In the King's Chamber, the granite beams above the chamber roof bear immense compressive load from overlying masonry. Load redistribution due to temperature change or minor settlement introduces incremental stress variation. Each incremental change could, in theory, produce microvoltage events. Without conductive circuitry to collect these events, they remain localized phenomena dissipating internally. Quartz watches rely on precisely cut crystals oscillating at stable frequencies when energized. Their performance depends on uniform orientation and minimal damping. Granite lacks this engineered precision. Nevertheless, the fundamental physics remains identical. Mechanical deformation produces electric polarization. The difference lies in optimization, not principle. Microphones similarly exploit piezoelectric materials to translate pressure waves into signal. The King's Chamber granite, under acoustic excitation, undergoes pressure fluctuation, albeit at low amplitude relative to microphone diaphragms. The potential interplay between granite and limestone resembles that between active and passive materials in composite systems. Limestone's relative insulation may prevent rapid charge equalization between granite surfaces and surrounding mass. However, humidity within the chamber and contact interfaces likely provide leakage paths. Over time, any generated charge dissipates. The absence of metal conductors within the structure precludes sustained electrical output. Piezoelectric granite therefore occupies a middle ground between inert stone and engineered device. It is responsive but not optimized. It can generate micropotentials under dynamic strain, but cannot produce macroscopic energy without collection mechanisms. Recognizing this avoids fantasy while acknowledging measurable physics. The narrative edges toward material science because the phenomenon belongs there. Measurements of granite resistivity show values varying with moisture content. Dry granite exhibits high resistivity, limiting current flow. Moisture lowers resistivity by enabling ionic conduction along grain boundaries. In subterranean or humid conditions, charge mobility increases slightly, yet the magnitude remains small compared to engineered conductors. Thus, any microcharge produced within granite blocks likely dissipates locally rather than forming sustained current pathways. The combination of pressure, vibration, and quartz content creates a scenario where microscale electrical activity accompanies mechanical stress. Whether ancient builders recognize such subtle effects cannot be determined from physical evidence alone. What can be stated confidently is that granite is not electrically inert under stress. Its quartz fraction ensures responsiveness to deformation. Material science frames the discussion without extrapolation. Granite's piezoelectric response is real but limited. Massive blocks amplify volume, but not necessarily net voltage due to orientation randomness. Limestone surrounding granite modifies electrical boundary conditions, but does not transform the system into a generator. Acoustic resonance within chambers introduces dynamic strain capable of triggering micropotentials, yet the scale remains modest. In summary, quartz within granite links mechanical stress to electrical potential through established physical law. Modern devices harness this link deliberately. In ancient granite architecture, the link exists passively as a property of material composition. Massive granite blocks subjected to load, vibration, and thermal cycling likely produce transient microcharge events. The contrast between granite and limestone influences how these charges distribute and dissipate. This perspective remains grounded in measurable physics, acknowledging the subtle electrical behavior of stone without attributing to it capabilities beyond material science. In October 2015, before sunrise cooled the Giza plateau, a team participating in the Scan Pyramids project aimed high-resolution infrared cameras at the faces of the Great Pyramid. The objective was straightforward: detect temperature differentials across the stone surfaces that might indicate hidden voids, structural irregularities, or material inconsistencies. Infrared thermography is a well-established diagnostic tool in engineering. Differences in thermal emission can reveal density changes, air pockets, or variations in heat retention. No one expected spectacle. The expectation was data, gradients, maps, incremental deviations measured in degrees Celsius. What emerged from those early scans were localized hotspots near the pyramid's eastern base and along specific blocks that displayed temperature differences of several degrees compared to adjacent stones. At dawn, when surface temperature typically stabilizes after night cooling, certain limestone blocks appeared warmer than neighboring ones without obvious structural explanation. The variation was not diffuse. It was concentrated, forming patterns rather than random scatter. This observation did not confirm hidden chambers, nor did it imply internal machinery. It indicated that thermal behavior at specific points deviated from surrounding stone under identical environmental conditions. Temperature variation without visible cause unsettles researchers because stone mass generally equalizes thermal distribution predictably. Limestone absorbs solar heat during the day and radiates it gradually at night. When conditions remain uniform, identical material, thickness, exposure, adjacent blocks should cool at similar rates. The detected anomalies suggested that something beneath or within certain blocks altered heat flow. Possible explanations included voids, air currents, density changes, or moisture differentials. Each carries implications about internal structure. Infrared imaging detects emitted radiation proportional to surface temperature. When a block retains more heat, it radiates more strongly in the infrared spectrum. If underlying cavities trap warm air, convection currents can alter surface temperature distribution. Conversely, denser stone may retain heat differently from porous sections. In the 2015 scans, the anomalies clustered in regions not previously associated with known cavities. This raised the possibility that internal architectural features remained undocumented. Convection versus energy retention became central to interpretation. Convection involves movement of air or fluid transferring heat through circulation. If internal voids exist behind a stone block, trapped air could warm during daylight and release heat slowly at night, creating surface temperature differences. Energy retention, by contrast, refers to intrinsic material properties causing certain blocks to store heat longer due to composition or thickness variation. Distinguishing between these requires repeated measurements under varying environmental conditions. Researchers returned at different times of day to observe whether anomalies persisted or shifted. Consistency strengthens structural explanations. Variability suggests environmental influence. Initial reports indicated that some hotspots remained stable across multiple scans, while others fluctuated with external temperature changes. Stability implies that subsurface conditions, voids or structural irregularities, may influence heat transfer. Fluctuation aligns more closely with surface effects such as moisture evaporation or uneven solar exposure. The data unsettled researchers not because it confirmed extraordinary claims, but because it introduced complexity into a structure long assumed fully mapped. The Great Pyramid has been studied intensively for centuries. Any suggestion of unknown internal features invites scrutiny. Infrared anomalies do not reveal precise geometry. They hint at discontinuities in thermal conductivity. That hint alone justifies further investigation using complementary techniques, such as muon tomography or ground-penetrating radar. Muon detection, deployed in subsequent phases of the Scan Pyramids project, identified previously unknown voids within the pyramid's core, including a large cavity above the Grand Gallery. Although this void's discovery did not directly correlate with the initial thermal anomalies at the base, it reinforced the notion that internal architecture remains partially hidden. Thermal scanning thus served as an entry point into renewed structural inquiry. Heat and vibration correlation speculation emerged in parallel discussions. Granite and limestone respond differently to thermal stress. Temperature change induces expansion and contraction. Differential expansion between adjacent blocks can produce microstrain. If subsurface cavities alter airflow patterns, localized temperature gradients may fluctuate rhythmically with environmental cycles. Such rhythmic change could introduce periodic mechanical stress into the stone mass. While minor compared to structural load, repeated cycles accumulate effects over long durations. Some researchers proposed that the pyramid's internal voids act as thermal buffers, storing heat during the day and releasing it slowly at night. If air movement within these voids occurs, convection currents could circulate heat unevenly. In enclosed cavities, temperature gradients generate pressure differences that drive air motion. That motion, in turn, exerts small dynamic forces on surrounding stone surfaces. Over time, such forces may contribute to vibrational signatures measurable by sensitive equipment. Infrared hotspots also invite consideration of material heterogeneity. Limestone blocks used in the pyramid vary in density and porosity depending on quarry source. Blocks with lower porosity retain heat differently from more porous ones. Microfractures within stone can trap moisture, altering thermal conductivity. When moisture evaporates, latent heat exchange modifies surface temperature. The 2015 scans captured patterns that may reflect subtle variations in material properties, invisible to the naked eye. Researchers emphasized caution. Thermal imaging is sensitive to environmental noise, wind, solar angle, atmospheric conditions. Dawn measurements minimize direct solar interference. Yet residual heat from previous days' exposure can persist unevenly. To attribute anomalies to structural voids requires elimination of surface-level explanations. This process demands repeated scanning across seasons and comparison with structural modeling. Nevertheless, the visual impact of the infrared images captured public attention. Color gradients revealed blocks glowing warmer than neighbors, suggesting hidden irregularities. For engineers, the images represented a dataset requiring analysis rather than spectacle. Temperature differentials of several degrees are significant in stone structures, particularly when localized. Such variation implies altered heat flow paths. In structural engineering, thermal anomalies can reveal stress concentration zones. Areas retaining more heat may correspond to thicker stone or reduced ventilation. If a block overlays an internal cavity, air circulation behind it may insulate the surface differently. The challenge lies in differentiating between superficial and structural causes. Finite element modeling can simulate expected thermal behavior given known geometry. deviations between model and observation highlight areas for deeper investigation. Heat retention intersects with vibration in subtle ways. Thermal expansion modifies stress distribution within stone. As temperature rises, expansion increases compressive stress along contact surfaces. As it falls, contraction reduces stress. Cyclic expansion and contraction may alter modal frequencies of structural components slightly. Though changes are minute, long-term monitoring can detect shifts in vibrational behavior correlated with temperature variation. In the context of piezoelectric granite, temperature change also influences electrical behavior. Thermal strain within quartz crystals generates stress, potentially producing micropotentials. Again, magnitude remains small, yet the coupling between heat, strain, and electrical response exists physically. Infrared anomalies therefore contribute indirectly to discussions about dynamic material interaction within the pyramid. The 2015 thermal scan unsettled researchers primarily because it demonstrated that the Great Pyramid is not thermally uniform. Even in a structure as monumental and seemingly static as Khufu's pyramid, dynamic processes occur daily. Heat flows through stone, air circulates within cavities, and material properties influence distribution. Infrared imaging provided a snapshot of this dynamic system. Subsequent analysis sought to correlate hotspots with known internal architecture. Some anomalies aligned with previously mapped voids, others did not. The large void above the Grand Gallery, identified later through muon tomography, may influence internal heat distribution indirectly. Air trapped within such spaces behaves differently from solid stone under diurnal temperature cycles. If air warms and cools more rapidly than stone, adjacent surfaces reflect that difference in thermal emission. The tension rising from modern data does not hinge on extraordinary claims. It stems from the realization that the pyramid remains partially opaque even to contemporary instrumentation. Infrared scanning revealed behavior not immediately explainable through simple surface inspection. That alone renews investigative momentum. Convection versus energy retention remains central to interpretation. If anomalies arise primarily from air movement within voids, they underscore architectural complexity. If they result from intrinsic stone variation, they highlight construction diversity. In either case, the data demonstrate that the pyramid's thermal profile is layered rather than uniform. Researchers continue to refine thermographic methodology, accounting for emissivity variations and environmental interference. Controlled measurements under different atmospheric conditions aim to isolate persistent structural signals. The goal is clarity, not sensationalism. Infrared hotspots represent starting points for inquiry, not conclusions. Heat interacting with vibration remains speculative but grounded in physics. Thermal cycles introduce mechanical strain. Mechanical strain influences resonance characteristics. If internal cavities and material contrasts create localized stress variation, they may subtly modify vibrational response. Whether such modification holds functional significance is unproven, yet measurable interactions between temperature and structural dynamics are well documented in engineering contexts. The 2015 scan thus marks a modern inflection point. It reintroduced empirical uncertainty into a monument long assumed thoroughly understood. Infrared imaging exposed non-uniform heat behavior. Subsequent muon detection confirmed hidden architectural spaces. Together, these findings illustrate that the Great Pyramid still contains unresolved structural complexity. Thermal anomalies do not imply hidden technology or active energy systems. They indicate that environmental and structural variables interact within the pyramid's mass. Stone absorbs, stores, and releases heat in patterns influenced by geometry and internal voids. Temperature variation without visible cause prompts investigation precisely because the structure appears static. As infrared cameras continue to probe ancient monuments, the data accumulate quietly. Each scan adds layers of measurable behavior: heat flow, material response, environmental interaction. The Great Pyramid's 2015 thermal anomalies serve as a reminder that even the most studied structures remain dynamic systems shaped by physics. Modern instruments do not dissolve mystery entirely. They refine it into datasets demanding careful interpretation. When engineer Christopher Dunn began constructing scale models of the Great Pyramid, he was not attempting to recreate mythology. He was testing geometry. His premise was simple. If the pyramid's internal configuration and material composition interact with environmental forces in measurable ways, then scaled-down replicas might display proportional effects. Scale modeling is a common engineering practice. Aircraft, bridges, and turbines are routinely tested in miniature to observe behavior under controlled conditions. Dunn applied that same logic to pyramid architecture, fabricating reduced-scale models incorporating key internal chambers and passages. The models varied in material depending on the experiment. Some were constructed from limestone analogs, others from granite substitutes, to approximate density differences. Internal chambers such as the King's Chamber and Grand Gallery were reproduced with proportional dimensions scaled mathematically. The objective was not aesthetic fidelity, but geometric fidelity. If shape influences resonance or electrical behavior, maintaining proportional relationships should preserve scaled physical effects. One set of experiments focused on vibrational excitation. Dunn subjected the models to controlled acoustic frequencies matching scaled resonant values derived from the full-size structure. In acoustics, frequency scales inversely with dimension. A smaller chamber resonates at higher frequencies relative to its full-scale counterpart. By calculating these scaled frequencies, Dunn introduced sound waves to the model and measured response using sensitive microphones and piezoelectric sensors. Under certain resonant conditions, sensors attached to granite analog components detected transient voltage spikes in the millivolt range. These readings were small but above baseline noise when control frequencies were applied. When excitation frequency deviated from the calculated resonant band, voltage response diminished. This suggested a correlation between vibrational resonance and electrical output within the material. The observed magnitudes were modest, typically a few millivolts, but repeatable under similar conditions. Voltage spikes under resonance align with known piezoelectric behavior. When quartz-bearing materials experience periodic strain at resonant frequencies, mechanical oscillation intensifies, amplifying deformation at specific points. Amplified deformation increases charge displacement in piezoelectric crystals. The scale models, though composed of modern materials rather than ancient granite, replicated density and geometric relationships sufficiently to test this principle. The key observation was not magnitude but pattern. Electrical response increased at resonant alignment. Alignment sensitivity emerged as another notable factor. Small changes in model orientation relative to external electromagnetic fields appeared to influence sensor readings. Dunn rotated the models incrementally and recorded variations in detected voltage and magnetic flux using magnetometers. While environmental electromagnetic noise complicates interpretation, repeated orientation adjustments revealed fluctuations exceeding background variation in certain alignments. This sensitivity suggested that geometry and orientation could affect interaction with ambient fields. Millivolt readings and magnetic fluctuations were documented carefully. Dunn emphasized that the outputs were weak and did not imply large-scale energy generation. The signals detected required amplification and shielding to separate from environmental noise. However, the presence of measurable response under controlled resonance conditions indicated that geometric structure, combined with material composition, can influence electrical behavior. Critics of the experiments point to scaling limitations. Material properties do not always scale linearly with dimension. Grain orientation, internal damping, and construction precision differ between models and ancient monuments. Additionally, laboratory environments contain electromagnetic interference from wiring, equipment, and urban infrastructure. Dunn attempted to mitigate these variables through isolation and repeated trials, but complete elimination of external influence remains challenging. Despite these caveats, the experiments served as a conceptual bridge. They demonstrated that resonance within a geometrically faithful model could coincide with measurable electrical response. This does not prove that the Great Pyramid functioned as an energy device. It establishes that stone structures containing quartz and shaped according to specific proportions can exhibit coupled mechanical electrical behavior when excited appropriately. Magnetic fluctuations detected during testing were subtle. Magnetometers recorded micro-Tesla level variations correlated temporally with acoustic excitation. Such fluctuations could result from movement of charge within the material or from sensor interference due to vibration. Distinguishing between these possibilities requires rigorous control experiments. Dunn acknowledged the ambiguity, presenting findings as suggestive rather than definitive. Scale pyramid models also allowed examination of internal airflow and pressure distribution. By introducing smoke or tracer particles into scaled passages, researchers observed convection patterns influenced by chamber geometry. These patterns inform understanding of how environmental factors might interact with structural cavities in the full-scale pyramid. While not directly tied to electrical output, airflow influences acoustic and thermal behavior, which in turn affect mechanical strain. The significance of alignment sensitivity warrants cautious interpretation. The Great Pyramid is oriented with remarkable precision relative to cardinal directions. Whether this orientation influences interaction with Earth's magnetic field remains speculative. In scale tests, slight rotational adjustments produced measurable changes in sensor output, but separating true geomagnetic interaction from experimental artifact is complex. The Earth's magnetic field at Giza is relatively weak compared to artificial sources present in modern environments. Therefore, extrapolating model behavior to ancient context requires restraint. Millivolt readings under resonance are consistent with piezoelectric activation. The amplitude depends on strain magnitude, material composition, and sensor placement. In full-scale granite blocks, strain amplitude from acoustic resonance is small relative to structural load. Yet cumulative quartz volume could generate distributed micropotentials under dynamic excitation. Whether these potentials would combine constructively or cancel due to grain orientation remains unresolved. Correlation without proof defines the boundary of the Dunn experiments. Observed electrical response coincided with resonant vibration in scale models. However, correlation does not establish intent, function, or historical application. It confirms that geometry and material properties can interact in measurable ways. Translating this interaction into claims about ancient purpose exceeds available evidence. The engineering value of the experiments lies in methodology. By constructing proportional models and subjecting them to controlled excitation, Dunn applied modern analytical techniques to ancient design questions. Even if conclusions remain tentative, the approach exemplifies empirical exploration rather than conjecture. Replication by independent researchers would strengthen or refine findings. Scaling laws complicate direct inference. Acoustic frequency scales inversely with dimension, but electrical properties depend on material microstructure independent of size. In models built from contemporary stone or composites, grain alignment and impurity distribution differ from Aswan granite. These differences influence piezoelectric response. Therefore, quantitative equivalence between model and monument cannot be assumed. Nevertheless, the bridge between ancient precision and modern recreation rests on shared physics. Granite contains quartz. Quartz under strain produces electrical potential. Geometry shapes resonance. Resonance amplifies strain at specific frequencies. These principles operate regardless of historical context. Dunn's experiments explore their intersection within pyramid-like configurations. Voltage spikes recorded in millivolts represent low-level phenomena requiring amplification. In practical engineering applications, such signals could be harnessed with electrodes and conductive pathways. The pyramid lacks known wiring or conductive infrastructure. Therefore, even if micropotentials occurred within its granite chambers, collection mechanisms remain absent from archaeological record. Magnetic fluctuations observed during testing remain ambiguous. Movement of charge can induce magnetic fields according to Maxwell's equations. However, sensor vibration or external interference can produce similar readings. Dunn interpreted these fluctuations as potential evidence of dynamic coupling between mechanical and electromagnetic domains. Critics argue that experimental noise may account for the signals. Alignment sensitivity intersects with architectural orientation. The pyramid's cardinal alignment within a fraction of a degree suggests astronomical precision. Whether such alignment influences electrical or magnetic interaction is uncertain. Earth's magnetic field varies regionally and temporally. Ancient orientation methods likely relied on stellar observation rather than magnetic compass. Thus, electrical alignment hypotheses require cautious framing. Scale models provided a controllable environment to test hypotheses about geometry-driven effects. By isolating variables such as chamber dimension, material type, and excitation frequency, Dunn explored relationships difficult to observe directly within the monument. Though limitations persist, the experiments demonstrate that structural form influences measurable physical phenomena beyond static load. In engineering research, preliminary findings invite replication. The Dunn experiments have not yet been widely reproduced in independent laboratories, leaving their broader acceptance tentative. Still, they contribute to ongoing dialogue about how ancient structures interact with environmental forces. The bridge between ancient precision and modern recreation rests not on definitive proof, but on continuity of physical law. Geometry shapes vibration. Vibration influences material strain. Strain can produce electrical potential in quartz-bearing stone. Scale models illustrate this chain under controlled conditions. Whether the ancient builders intended such interaction remains unanswered. What remains clear is that modern experimentation can probe the physical behavior of forms conceived millennia ago. Correlation without proof preserves scientific caution. The presence of voltage spikes under resonance in scale pyramids does not confirm function in full-scale monuments. It indicates possibility grounded in material science. As with thermal anomalies and acoustic resonance, the data point toward complexity rather than conclusion. Modern recreation thus becomes a lens through which ancient precision is re-examined, not rewritten.
At the end of the 19th century, Nikola Tesla stood in a laboratory lit by arcs of violet discharge and spoke about the Earth as though it were not merely soil and stone, but a resonant body capable of carrying oscillation across continents. He did not speak the language of mysticism. He spoke of frequency, nodes, grounding, and standing waves. Tesla's experiments in Colorado Springs and later at Wardenclyffe centered on a simple but radical premise, that energy could be transmitted through the Earth itself if one understood how to excite it at the right frequency. To him, the planet was not passive mass. It was a conductor embedded in a vast electromagnetic system. Tesla's resonance experiments relied on tuned circuit coils calibrated to specific frequencies that would oscillate in harmony with larger systems. When an electrical oscillator matches the natural frequency of another body, energy transfer becomes dramatically more efficient. This principle, resonance, appears everywhere in physics. A tuning fork vibrates sympathetically when exposed to its matching tone. A bridge sways more violently when wind gusts align with its natural frequency. In Tesla's view, the Earth itself possessed natural frequencies determined by its dimensions and conductivity. By injecting oscillations at these frequencies, he believed energy could propagate as standing waves along the planet's surface. Standing waves form when waves reflect and interfere constructively, producing stationary nodes and antinodes. In a bounded system, such as a cavity or along a conductive surface, certain wavelengths align precisely with boundary conditions, reinforcing rather than dissipating. Tesla theorized that by grounding one end of a transmitter deeply into the Earth and elevating the other into the atmosphere, he could create oscillatory currents that traveled globally, returning in phase at predictable intervals. Whether his larger ambition succeeded remains debated, but his conceptual framework centered on frequency as governing principle. Grounding played a critical role in Tesla's apparatus. He drove metal rods deep into soil to establish low-resistance contact with the Earth, ensuring that oscillations could couple effectively into the planetary body. Without grounding, energy dissipates locally. With grounding, it can propagate along conductive paths. Tesla described the Earth not as an infinite sink, but as a medium capable of sustaining oscillatory patterns under the right conditions. The relevance of Tesla's language to ancient stone architecture lies not in direct historical connection, but in shared physical logic. Granite chambers resonating acoustically, limestone foundations interacting with groundwater, quartz crystals generating micropotentials under strain. These phenomena reflect the same underlying principle Tesla pursued, that matter responds selectively to frequency. Resonance is not modern invention. It is intrinsic property of physical systems. Tesla's mechanical oscillator experiments provide a striking illustration. He constructed devices that, when tuned to a building's resonant frequency, induced perceptible vibration with minimal input power. The phenomenon did not require overwhelming force. It required matching frequency. In such cases, energy accumulates over cycles rather than arriving in a single impulse. This accumulation underlies the concept of harmonic reinforcement observed in pyramid chambers. The Earth as conductor concept extends beyond electromagnetism. In seismology, the planet transmits mechanical waves from earthquakes across vast distances. These waves travel through rock layers, reflecting and refracting according to material properties. Certain frequencies persist longer than others due to resonance within geological structures. Tesla's broader insight was that large-scale bodies possess modal characteristics like smaller objects. Scale changes frequency range, but not principle. Standing waves and grounding intersect conceptually with pyramid architecture. The Great Pyramid rests directly upon bedrock, integrating its mass into the plateau. Granite chambers embedded within limestone create material contrasts analogous to conductive and resistive domains. While stone does not conduct electricity as metal does, it transmits mechanical vibration efficiently. If environmental forces such as groundwater movement or seismic microtremors introduce periodic excitation, the pyramid could respond according to its structural modes. Tesla approached resonance deliberately. He calculated coil dimensions to achieve specific oscillatory behavior. Ancient builders, if they engaged with resonance, would have approached it empirically. Sound within a chamber, vibration of stone under chant, or stability of massive blocks might reveal preferred proportions over generations. Frequency as design principle need not imply explicit mathematical formulae. It may arise from iterative refinement guided by sensory feedback. The parallels in material logic become clearer when considering Tesla's use of quartz in oscillators. Quartz crystals, when cut along precise axes, oscillate predictably under applied voltage. The King's Chamber granite contains quartz dispersed randomly, not engineered for uniform oscillation. Yet the shared property of quartz responding to stress bridges conceptual space between ancient material choice and modern frequency devices. Granite's durability and acoustic reflectivity may have been valued for reasons unrelated to electricity, yet its composition carries inherent frequency responsiveness. Tesla's philosophy emphasized harmony between engineered systems and natural frequencies. He argued that aligning with existing resonances minimizes energy expenditure. This concept echoes in architectural acoustics, where room dimensions determine tonal character. The King's Chamber reinforcing certain frequencies exemplifies how geometry shapes response. Whether intentionally tuned or incidentally resonant, the chamber embodies frequency-dependent behavior. Grounding in Tesla's experiments ensured that oscillations coupled to Earth rather than dissipating in air. In pyramid construction, grounding occurs physically through integration with bedrock. The structure is not isolated atop loose soil. It anchors into limestone foundation. This anchoring ensures mechanical continuity between monument and plateau. If vibrational energy enters the system from environmental sources, grounding determines how it distributes. Tesla envisioned global transmission, whereas pyramids remain localized. Yet both involve scale interacting with frequency. The size of the system dictates its natural modes. The Earth's circumference yields frequencies in extremely low ranges. A granite chamber meters in length resonates at audible frequencies. Though separated by orders of magnitude, both operate under the same wave equations. Frequency as design principle extends beyond acoustics and electricity. Structural stability depends on avoiding resonance with destructive forces. Engineers today calculate building natural frequencies to prevent collapse during earthquakes or wind loading. Ancient builders may have recognized empirically that certain proportions resist vibration more effectively. If a structure rings excessively under wind or ground tremor, its design invites modification. Over generations, practical adjustments can converge on frequency-aware forms. Tesla's Wardenclyffe Tower sought to transmit energy wirelessly by exploiting standing waves between Earth and ionosphere. The project remained incomplete, yet its conceptual ambition illustrates belief in resonance as universal mechanism. While no evidence suggests pyramids functioned as transmission towers, their geometry and mass inevitably interact with environmental frequencies. The philosophical bridge lies in recognizing that form governs response. Standing waves require boundary conditions. In the King's Chamber, granite walls provide rigid boundaries for acoustic modes. In Tesla's coils, conductive loops define electrical oscillation. Both systems illustrate how containment and proportion influence vibrational behavior. The mathematics describing them differ in domain, but converge in principle. Parallels in material logic should not be overstated. Tesla operated within electromagnetic theory articulated by Maxwell. Ancient builders left no texts describing wave equations. Yet physical law operates independent of articulation. If granite chambers resonate audibly, that resonance exists whether or not designers framed it mathematically. Tesla's work demonstrates that exploiting resonance can produce significant effects from modest input. Broadening the philosophical scope does not imply equating ancient monuments with modern electrical devices. It situates them within continuum of frequency-responsive systems. Stone, water, air, and earth itself all participate in vibrational exchange. The pyramid, by virtue of scale and integration, interacts with these exchanges. Tesla once remarked that if one wishes to understand the universe, one should think in terms of energy, frequency, and vibration. While the phrase is often quoted loosely, its essence reflects scientific observation. Oscillation underlies phenomena from atomic transitions to planetary motion. The pyramid's acoustic behavior, granite's piezoelectric response, groundwater-induced tremors all fit within this oscillatory framework. Frequency as design principle suggests that geometry matters not only for stability and aesthetics, but for dynamic response. Whether consciously applied or empirically discovered, alignment with resonant behavior shapes experience within architectural space. The King's Chamber amplifying certain tones exemplifies this. In modern laboratories, resonance is engineered with precision. In ancient stonework, resonance emerges from proportion and material choice. Tesla's experiments provide a vocabulary grounding, standing waves, harmonic reinforcement that clarifies how physical systems behave under oscillation. Applying that vocabulary to pyramid analysis enriches interpretation without asserting direct connection. The Earth as conductor concept reminds us that structures rest within larger systems. Mechanical waves traverse bedrock. Electromagnetic fields envelop monuments. Temperature cycles induce strain. These inputs constitute background frequencies influencing material behavior. Whether ancient architects designed with awareness of such phenomena remains uncertain, but their monuments inevitably participate. By situating pyramid architecture within the broader language of frequency articulated by Tesla, the inquiry shifts from isolated anomaly to universal principle. Stone resonates. Quartz responds to stress. Grounding shapes distribution. Standing waves reinforce alignment. The philosophical expansion lies in recognizing that resonance is not esoteric. It is embedded in the fabric of matter. Tesla sought to harness resonance deliberately. Ancient builders, through craft and proportion, created structures that exhibit resonant properties. The connection rests not on shared intention, but on shared physics. Frequency governs interaction between energy and form. Whether in a laboratory coil or a granite chamber, alignment with natural modes determines behavior. Thus, Tesla's resonance experiments illuminate the conceptual terrain in which pyramid anomalies reside. They provide modern vocabulary for phenomena observed in stone. Earth as conductor, standing waves. Grounding, these terms describe relationships between geometry, material, and vibration. In broadening the scope, we see ancient precision not as isolated achievement, but as manifestation of universal laws that later engineers, like Tesla, articulated explicitly.
Precision in stone is not confined to the Nile Valley. When viewed against a broader geographical canvas, similar anomalies appear across continents, separated by oceans and centuries, yet bound by a common material language. At Pumapunku in Bolivia, high on the Altiplano near Lake Titicaca, andesite and red sandstone blocks lie scattered across a wind-swept plateau. Some of these blocks exhibit right angles and flat planes so sharply defined that early 20th century explorers questioned how pre-Columbian tools could achieve such crisp geometry. The stone is hard, volcanic, and resistant, yet certain blocks contain internal corners cut to tolerances that approach modern masonry standards. Grooves intersect at precise 90-degree angles. Channels terminate cleanly without overcut. The repetition of these geometric features across multiple stones suggests systematic method rather than isolated craftsmanship. Laser scanning conducted in recent decades has quantified surface flatness and angular precision at Pumapunku. Measurements indicate that certain cut faces deviate from planar alignment by less than a millimeter over significant lengths. This does not imply machine tooling in the modern sense, but it confirms disciplined execution. The stones were not merely broken and fitted, they were shaped to interact modularly. The H-shaped blocks, often cited for their complexity, exhibit consistent dimensions that imply standardized production. Standardization reflects planning. Planning reflects process. Across the Mediterranean and Lebanon, the Baalbek temple complex presents another extreme of mass and manipulation. In the quarry near Baalbek rests the Stone of the Pregnant Woman, an unfinished limestone block estimated to weigh over 1,000 tons. Nearby, additional monoliths approach similar magnitude. Within the Temple of Jupiter's podium, trilithon stones each weighing hundreds of tons are positioned several meters above ground level. The stone's surfaces are not polished to mirror finish, yet their placement displays controlled alignment. Gaps between blocks are minimal. Joint faces are carefully dressed to ensure stable seating. The logistical feat of moving and placing such stones commands attention, but equally striking is the precision with which they interlock. In certain sections, stone faces conform tightly, despite their immense weight. Achieving this fit requires accurate leveling and surface preparation. Limestone, softer than granite, allows easier shaping, yet controlling flatness over multi-ton blocks remains challenging. The Baalbek monoliths demonstrate that large-scale stone manipulation was not exclusive to one culture. In Japan, seismic resilience has shaped architectural tradition for centuries. The stone walls of Himeji Castle and other fortifications employ precisely fitted stones arranged without mortar. The stones vary in shape but conform tightly, distributing load and accommodating seismic motion. Unlike rigid masonry bound with cement, these walls flex subtly under earthquake stress. Their stability arises not from adhesive bonding, but from geometric interlocking and mass distribution. The precision lies not in perfect right angles, but in tailored fit. Each stone's contour complements its neighbors, creating a self-stabilizing assembly. Japanese stonecraft emphasizes adaptive geometry. Rather than forcing uniform blocks into place, masons select and shape stones to interlock naturally. The resulting walls appear irregular yet function as cohesive systems. During seismic events, slight shifts occur, but collapse is rare. The design principle recognizes dynamic forces rather than static idealization. Precision here manifests as responsiveness rather than polish. In Ireland, scattered across megalithic landscapes, certain standing stones and chambered cairns exhibit acoustic properties that earned them the informal designation singing stones. At sites such as Newgrange and Noath, tapping specific stones produces resonant tones distinct from surrounding rock. The resonance arises from material density, internal structure, and placement within chamber geometry. Though modest compared to pyramid acoustics, the phenomenon suggests sensitivity to sound in prehistoric construction. Some Irish passage tombs align with solstitial sunlight, indicating astronomical awareness. Their chambers, often lined with carefully selected stone slabs, amplify low-frequency sounds during ritual activity. The stones themselves do not sing spontaneously. They respond when excited. This responsiveness parallels acoustic behavior observed in Egyptian granite chambers, though on smaller scale. Independent convergence versus shared logic becomes central when comparing these global examples. Pumapunku's angular precision, Baalbek's mass manipulation, Japan's seismic interlocking, Ireland's resonant chambers, each arises within distinct cultural and temporal contexts. Direct transmission of technique across such distances lacks supporting evidence. Yet commonalities emerge in how stone responds to geometry and force. Material properties constrain and enable possibilities. Andesite at Pumapunku requires controlled abrasion to achieve crisp edges. Limestone at Baalbek permits large-scale shaping but demands careful leveling. Granite in Egypt reflects sound efficiently and withstands compression. In Japan, variable stone shapes accommodate seismic motion. In Ireland, dense slabs resonate under impact. Each culture exploited the intrinsic behavior of available material. Precision across continents may therefore reflect independent solutions to similar physical challenges, rather than evidence of shared hidden technology. Human cognition, confronted with stone's resistance and potential, tends to iterate toward methods that optimize control. Straight lines distribute load predictably. Flat planes ensure stable contact. Interlocking shapes resist displacement. Resonant chambers amplify voice. These outcomes follow from engagement with physics rather than cultural coincidence alone. Yet the recurrence of extreme precision invites deeper reflection. Pumapunku's modular stone blocks suggest a system of measurement and replication. Baalbek's trilithons indicate confidence in managing weight at monumental scale. Japanese seismic walls reveal empirical understanding of vibration and flexibility. Irish chamber acoustics imply sensitivity to sound within stone enclosures. None of these require mystical explanation, yet together they illustrate that ancient builders across the globe engaged stone as active medium rather than inert mass. Global echoes in stone do not necessarily indicate a lost global civilization sharing secret knowledge. They demonstrate that when humans push material to its limits, similar patterns emerge. Precision arises where control matters. Resonance appears where geometry and material align. Mass challenges inspire innovation. Independent convergence is a well-documented phenomenon in technological evolution. Agricultural tools, for instance, evolved similarly in regions without contact because soil and crop physics dictate function. Shared logic operates beneath cultural expression. Stone obeys the same mechanical laws in Bolivia as in Egypt. Gravity exerts identical acceleration in Lebanon and Japan. Acoustic resonance follows universal wave equations. When builders experiment with these constraints over generations, they may converge on similar principles without communication. At Pumapunku, debate continues over how andesite blocks were cut. Proposed methods include hammerstones, copper tools with abrasives, and potential use of harder stone implements. Regardless of specific tools, the measured precision indicates deliberate process. In Baalbek, Roman engineering capabilities are better documented, yet the scale of the trilithon still provokes discussion. In Japan, historical records detail masonry techniques adapted to seismic risk. In Ireland, archaeological evidence links chamber design to ritual acoustics. The planetary pattern does not demand a single origin story. It underscores that stone, when treated with sustained focus, reveals latent possibilities. The mystery becomes less about isolated anomaly and more about distributed ingenuity responding to shared physical reality. Modern scanning technologies applied globally reinforce this perspective. Laser mapping at Pumapunku quantifies tolerances. Structural analysis at Baalbek assesses load distribution. Seismic modeling of Japanese walls demonstrates dynamic performance. Acoustic measurement in Irish tombs documents resonant frequencies. These datasets transform anecdote into comparative framework. Precision, mass, resonance, and interlocking geometry form recurring themes. Each site expresses them differently. Egyptian granite chambers emphasize interior polish and acoustic reinforcement. Andean blocks highlight modular repetition. Levantine monoliths showcase scale. Japanese walls illustrate flexibility. Irish stones echo under touch. The planetary dimension reframes inquiry. Instead of isolating Egypt as singular anomaly, we observe a spectrum of ancient material mastery. The absence of direct connection does not diminish significance. It suggests that certain thresholds of craftsmanship are attainable when societies invest resources and knowledge into stone manipulation. Independent convergence offers plausible explanation. Human experimentation under similar constraints yields analogous solutions. Shared logic of physics guides outcomes. Stone invites shaping. Resonance invites tuning. Mass demands leverage. Geometry governs stability. Across continents, builders encountered these realities and responded creatively. Global echoes in stone therefore broaden the narrative from local mystery to universal exploration. Ancient precision appears not as aberration but as distributed manifestation of engagement with material law. The recurrence of high-tolerance surfaces, massive blocks, and resonant chambers reflects persistent curiosity about how matter behaves under force and proportion. The mystery becomes planetary, not because it points to hidden coordination, but because it highlights common pursuit of mastery over stone. When measured with modern instruments, these monuments reveal patterns rooted in physics rather than folklore. The world's ancient builders, separated by oceans and epochs, each negotiated with gravity, vibration, and geometry. Their solutions differ in style, yet converge in principle, reminding us that stone, wherever found, answers to the same universal equations.
When precision appears early in a civilization's material record, and then softens in later periods, historians confront an uncomfortable inversion of the expected narrative. Progress typically trends toward refinement. Tools improve, methods accelerate, tolerances tighten. Yet in Egypt, the most exact granite work clusters in the Old Kingdom, particularly during the 4th dynasty, when the Great Pyramid and associated structures were constructed. Measurements of casing stones, internal chamber joints, and granite artifacts from this era reveal tight tolerances that are difficult to reconcile with the accepted toolkit of copper chisels, dolerite pounders, wooden sledges, and sand abrasives. In contrast, many monuments of the New Kingdom and later periods, though elaborate in decoration and scale, display comparatively looser stone joints and less rigorous surface flatness in hard granite applications. The regression is not universal, but it is measurable. The question that follows is not sensational, but methodological. Why would a culture capable of high-precision stonecraft allow that capability to diminish? One explanation centers on guild knowledge and oral transmission. In ancient Egypt, specialized crafts were often organized into tightly controlled workshops tied to royal or temple patronage. Master masons trained apprentices through demonstration and repetition rather than written manuals. Tool techniques, sequencing of cuts, and subtle handling methods likely passed from generation to generation as embodied knowledge rather than codified procedure. Such transmission can preserve remarkable skill so long as institutional continuity remains intact. However, it is also fragile. Disruptions in political stability, shifts in patronage, or economic strain can dissolve workshop lineages within a few decades. If the highest precision granite techniques were confined to elite crews attached to specific pharaonic projects, their dissolution could mean the rapid disappearance of specialized practices that had no written record. The Old Kingdom centralized resources in unprecedented ways. Royal authority commanded labor, materials, and logistics on a scale rarely matched in later centuries. Monumental projects such as the Giza pyramids required coordinated quarrying, transport, shaping, and placement under strict oversight. Such concentration of effort fosters standardization and refinement. When thousands of blocks must conform to a geometric master plan, deviations become intolerable. In this environment, measurement systems tighten, templates proliferate, and best practices solidify. After the collapse of Old Kingdom central authority around the end of the 6th dynasty, Egypt entered the first intermediate period, marked by fragmentation and regional power shifts. Monument building continued, but resources were dispersed among local rulers. Precision requiring centralized discipline may have eroded alongside political unity. Cultural priorities also evolved. The Old Kingdom invested heavily in megalithic permanence, large, geometrically severe forms intended to endure indefinitely. Later periods favored ornate temples, decorated tombs, and elaborate relief carving over monolithic granite interiors. Limestone and sandstone became more prevalent in surface architecture. Decorative complexity sometimes replaced structural extremity. The skill required to carve fine hieroglyphic relief differs from that needed to produce mirror-finished granite chambers. Craft specialization may have diversified rather than intensified in one direction. As aesthetic emphasis shifted, the highest levels of hard stone machining could have become less central to elite identity. Tool degradation over time presents another practical factor. Copper tools require frequent annealing and reshaping. Maintaining high-performance cutting edges demands consistent access to quality ore and controlled metallurgy. If copper supply fluctuated or metallurgical standards declined, tool effectiveness could suffer. Even minor changes in alloy composition influence hardness and durability. Although Egypt maintained copper production for centuries, trade disruptions or resource depletion might have reduced material quality available to certain workshops. Abrasive sands, too, vary in hardness and grain distribution. A change in quarry source could subtly affect surface finish outcomes. Experimental archaeology demonstrates that patience and labor can achieve significant results with simple tools. However, the difference between acceptable workmanship and extreme tolerance is not merely time but control. High precision depends on stable reference systems, calibrated measurement devices, and disciplined workflow. If measurement standards loosen or training shortens, tolerances expand quickly. Consider a mason who learns through demonstration how to maintain flatness within a fraction of a millimeter by checking against a master straightedge. If that master straightedge is lost, damaged, or no longer valued, subsequent generations may approximate rather than replicate its rigor. The knowledge does not vanish instantly. It dilutes. There is also the matter of economic incentive. Monumental precision is costly. It demands skilled labor, extended timelines, and sustained oversight. In periods where political legitimacy rested on rapid temple construction or territorial expansion, speed may have outranked perfection. Later dynasties built extensively, but their architectural goals differed. Large-scale projects at Karnak and Luxor prioritized grandeur and iconography. Granite elements remained, yet interior polish sometimes yielded to exterior spectacle. When evaluation criteria change, craft standards follow. Regression can be subtle rather than dramatic. Laser surveys of later granite sarcophagi show respectable workmanship, yet not always the orthogonality documented in certain Old Kingdom examples. Interior surfaces sometimes retain faint tool chatter or minor deviations in parallelism. These differences are not catastrophic. They are incremental. The question becomes whether they reflect lost technique or simple variation in ambition. Some scholars argue that the Old Kingdom examples represent exceptional state-sponsored efforts, unlikely to be repeated without similar political concentration. Guild secrecy may have amplified vulnerability. If advanced techniques were guarded within limited circles, their extinction risk increases. Written treatises on stone shaping from ancient Egypt are scarce. Hieroglyphic inscriptions celebrate royal achievements, but seldom detail construction processes. Reliefs depict quarrying scenes and labor organization, yet technical specifics remain minimal. The absence of manuals suggests reliance on apprenticeship. When apprenticeship chains break, tacit knowledge dissipates rapidly. Technological evolution does not always follow linear improvement. History offers numerous cases of regression when societal complexity shifts. Roman concrete formulations were partially forgotten after the empire's decline. Medieval European iron production techniques varied widely in quality. Knowledge persistence depends on institutional continuity as much as on innovation. In Egypt, repeated periods of upheaval, foreign invasions, internal strife, economic stress may have fractured specialized crafts. Environmental changes may have contributed indirectly. Quarry access can alter as flood patterns shift or sediment accumulates. If high-quality granite sources became more distant or difficult to exploit, workshops may have relied more heavily on softer stones. Over generations, proficiency in hard granite shaping could wane simply through reduced practice. Skills unused atrophy. There remains the possibility that what appears as regression reflects selective survival of evidence. Old Kingdom monuments built in durable granite endured with minimal alteration. Later structures, especially those of softer stone, eroded or were repurposed. Our comparison may be skewed toward the best preserved examples from early periods. Even so, documented cases of early precision exceeding later analogs warrant scrutiny. Was the method lost rather than evolved? That phrasing suggests abrupt disappearance, but loss often occurs gradually. Techniques can fragment into partial practices. A master mason's nuanced handling of abrasive slurry may survive in simplified form. Calibration routines may become less stringent. Measurement references may degrade. Over time, outputs diverge from original benchmarks without conscious recognition of decline. Cultural memory sometimes reinterprets lost expertise as myth. Later generations encountering exceptional Old Kingdom works might attribute them to divine assistance rather than human skill. Such reframing can discourage attempts at replication. If the early pyramids were perceived as achievements beyond mortal capacity, subsequent builders may have redirected ambition toward alternative expressions of devotion rather than striving to match precision. Tool evolution could also shift priorities. The introduction of bronze, though harder than copper, did not necessarily improve granite cutting efficiency without appropriate abrasives. Later iron usage in Egypt was limited and did not revolutionize quarrying immediately. Technological transitions are complex. Improved materials do not guarantee improved outcomes if systems integration falters. Another factor lies in administrative documentation. Old Kingdom projects likely maintained strict oversight, possibly including master measurement rods, plumb bobs, and leveling devices standardized across crews. Later decentralization might have reduced uniformity. Minor deviations accumulate when centralized calibration fades. The regression question invites humility. It challenges the assumption that technological capability always increases. Civilizations can plateau, redirect, or forget. The Old Kingdom may represent a peak in specific stonecraft disciplines, supported by political, economic, and cultural alignment. When those alignments shifted, the discipline softened. This does not imply vanished super technology or hidden machines. It highlights the fragility of specialized expertise. Precision is expensive to maintain. It requires institutional will, material quality, and generational continuity. Remove any element and tolerances expand. Ultimately, regression reframes the mystery. Instead of asking how early builders achieved such precision, we also ask why their successors did not consistently replicate it. The discomfort lies in acknowledging that human societies can misplace mastery. Knowledge need not be destroyed to disappear. It can erode quietly through neglect, distraction, or redirection. In the silent chambers of Saqqara in Giza, granite surfaces remain as fixed benchmarks of what once was possible. Later dynasties left monuments of equal cultural significance, but different technical emphasis. The comparison does not diminish their achievements. It underscores variability in human focus. Whether through lost guild lines, shifting aesthetics, degraded tools, or decentralized authority, the peak precision of the Old Kingdom stands as a reminder that expertise is not guaranteed to endure. It must be preserved intentionally, or it fades into stone, leaving only measured surfaces to testify that at one time, control exceeded what later generations deemed necessary or attainable. In the shadow of the Great Pyramid, two languages are spoken that rarely blend smoothly. One is the language of archaeology, patient, contextual, grounded in stratigraphy, tool fragments, inscriptions, logistics, and human labor. The other is the language of engineering, numerical, tolerance-driven, focused on force vectors, feed rates, material hardness, and measurable deviation. Both examine the same granite blocks, the same drill cores, the same sarcophagi. Yet they often arrive with different instincts about what the evidence means. At the center of the divide lies a deceptively simple contrast: patience versus torque. Archaeology asks how much time and coordinated labor can accomplish with simple tools. Engineering asks what kind of controlled force would be required to produce the patterns visible in stone. The disagreement is not about whether ancient Egyptians were capable, but about which mechanisms best explain the physical signatures left behind. The patience model begins with scale. Tens of thousands of workers organized in rotating crews, supplied with food, shelter, and supervision, can accomplish extraordinary tasks through repetition. Copper tools, though soft relative to granite, can function as carriers for abrasive slurry composed of quartz sand harder than the metal itself. In this view, the copper does not cut directly. It holds the abrasive that grinds away at the stone gradually. Experimental archaeology has demonstrated that granite can indeed be shaped through abrasion, given sufficient time. Channels can be carved, surfaces flattened, and even core drilling approximated using bow drills with abrasive feed. The process is slow and physically demanding, but not impossible. Archaeologists emphasize that ancient projects unfolded over decades, not days. Measured in years, small rates of material removal accumulate into monumental results. Engineering scrutiny enters when specific details are measured under magnification. Spiral grooves on certain granite cores display regular pitch and consistent depth progression. Interior faces of some granite boxes show tight parallelism across large surfaces. When engineers calculate the energy required to remove granite at the observed rates implied by groove spacing, they question whether hand-driven abrasion alone accounts for the uniformity. Torque, in machining terms, refers to rotational force applied consistently through a controlled mechanism. A constant feed rate describes the steady advance of a cutting tool into material per revolution. Engineers examining spiral cores often note that the groove spacing resembles a constant feed rate pattern more than an irregular hand-driven motion. The debate hinges on whether human arms can approximate such consistency under repetitive abrasion, or whether the pattern implies mechanical stabilization. Experimental abrasion studies have been central to the conversation. Researchers have constructed replica bow drills, copper tubes, and stone pounders to test granite shaping techniques. Results show that granite can be penetrated using quartz sand slurry and rotational motion. However, the surface finish often exhibits irregular microchatter, variable depth ridges, and uneven progression consistent with fluctuating pressure. Achieving high uniformity requires disciplined technique and careful monitoring. Some teams report success in producing relatively straight grooves, though typically at slower penetration rates than suggested by certain archaeological measurements. Other teams emphasize that ancient craftsmen, practicing from youth, might outperform modern experimenters lacking generational skill transmission. Here replication both succeeds and falters. It proves feasibility in principle, yet struggles to replicate extreme precision efficiently. Where replication succeeds most convincingly is in demonstrating transport and lifting logistics. Experiments with sledges on lubricated sand show that large stone blocks can be moved with coordinated labor. Ramps, levers, and counterweight systems plausibly account for placement. Quarry marks in Aswan match pounder impacts observed in modern reconstructions. Archaeology gains strength where physical traces align with replicable method. Where replication falters is often at the threshold of tolerance rather than possibility. Producing a flat surface is achievable. Producing a surface parallel within fractions of a millimeter across meters of granite is more challenging to replicate consistently using only abrasive techniques without rigid guiding systems. Engineers sometimes approach the problem backward. Instead of asking how ancient workers might have achieved the result, they calculate what modern machining setup would be required to produce similar tolerances efficiently. That analysis introduces concepts such as lathes, drill presses, and fixed axis rotation. Critics argue that this comparison risks anachronism, projecting contemporary industrial frameworks onto ancient contexts. Archaeologists caution that similarity in pattern does not necessitate identical mechanism. A spiral groove may resemble lathe work without having been produced by a powered lathe. Convergent patterns can arise from different processes. The divide persists because both sides possess valid constraints. Archaeology guards against speculative inflation. It insists that extraordinary claims require extraordinary evidence. No surviving artifact in Egypt definitively demonstrates powered rotary machinery. No inscriptions describe mechanical drill rigs. Tool assemblages recovered from sites include copper implements, stone pounders, and abrasives, not hardened steel bits or complex gearing. Engineering skepticism, on the other hand, resists accepting that uniform groove spacing automatically equates to hand variability. It asks whether repeated measurements across multiple artifacts imply process control beyond what intermittent manual correction could sustain. There is also a difference in training emphasis. Archaeologists are trained to contextualize artifacts within cultural frameworks to avoid isolating single anomalies from broader material culture. Engineers are trained to analyze systems behavior and tolerances independent of narrative. When engineers see identical pitch across cores, they interpret it as a signature of repeatable setup conditions. Archaeologists may interpret it as the result of consistent craft tradition using standardized tools. The same data generates two plausible readings. Where the conversation remains unresolved is in the absence of definitive disproof for either model. Abrasion experiments demonstrate feasibility, but not necessarily equivalence in efficiency. Mechanical interpretations demonstrate explanatory elegance, but lack direct archaeological corroboration. The evidence occupies a middle ground where neither dismissal nor dramatic escalation is warranted. Some propose hybrid models, weighted drills stabilized by simple frames, possibly using rope-driven rotation with abrasive slurry, providing more consistent feed without requiring advanced metallurgy. Such proposals aim to reconcile measurable uniformity with plausible toolkits. The danger of overreach is clear. When anomalies are exaggerated into proof of lost super-technology, credibility erodes. Invoking unknown machines without material evidence risks undermining legitimate inquiry. Sensational claims attract attention, but often obscure incremental, evidence-based progress. Overreach can alienate archaeologists, who might otherwise engage in collaborative testing. It can also encourage public misunderstanding of ancient capabilities, diminishing the demonstrated ingenuity of known methods. Equally present is the danger of dismissal. When measurable irregularities are waved away without thorough analysis, opportunities for refinement vanish. Intellectual stagnation occurs when anomalies are ignored because they complicate established narratives. Scientific progress often begins with discomfort around data that does not fit comfortably within existing models. Dismissal can prevent exploration of improved replication techniques or overlooked contextual factors such as tool stabilization methods not yet discovered. Intellectual honesty demands acknowledgement of uncertainty. Granite cores and sarcophagi exist as physical artifacts measurable by modern instruments. Copper tools and abrasives also exist in the archaeological record. The task is not to defend identity camps, but to test hypotheses rigorously. Engineering simulations can inform archaeological experiments. Archaeological context can constrain engineering speculation. Cross-disciplinary collaboration offers the best path forward. The divide also reflects differing tolerances for ambiguity. Archaeology often operates within probabilistic reasoning, accepting best-fit explanations given available evidence. Engineering seeks deterministic clarity, preferring measurable causal chains. When faced with incomplete data, archaeology may prioritize parsimony, while engineering may pursue alternative modeling until precision aligns with observation. Neither approach is inherently superior. Both are shaped by disciplinary norms. Ultimately, the debate over patience versus torque reveals more about modern epistemology than about ancient Egypt. It exposes how contemporary frameworks influence interpretation of the past. The granite does not argue. It presents surfaces and grooves. Humans project method onto them. The responsible stance lies between conviction and humility, recognizing that replication is ongoing and that ancient craft traditions may have included subtleties not yet fully reconstructed. The conversation endures because it rests on measurable artifacts rather than speculation alone. Spiral grooves can be scanned. Surface flatness can be quantified. Abrasion experiments can be repeated. Each iteration narrows uncertainty incrementally. The resolution may not arrive as a dramatic revelation, but as gradual convergence between replicated method and observed tolerance. In grounding this discussion, it is essential to avoid binary framing. The choice is not between primitive hand tools and advanced lost machines. The spectrum of possibility includes incremental refinements, stabilization rigs, improved abrasives, and disciplined craft culture. Engineering scrutiny need not imply ancient industrialization. Archaeological caution need not imply refusal to question. The divide, therefore, becomes productive rather than adversarial when approached with mutual respect. Patience and torque are not mutually exclusive metaphors. Ancient builders likely employed patience in abundance. Whether they also developed clever means of stabilizing torque remains open to investigation. The unresolved nature of the conversation is not a weakness. It is a reflection of honest inquiry. Precision in stone challenges modern assumptions. The proper response is neither to inflate nor to ignore, but to measure, test, refine, and remain willing to adjust models as evidence accumulates. Across deserts, jungles, high plateaus, and damp green fields, stone rises in forms that echo one another without sharing a common script. A pyramid on the Giza plateau leans toward true north with astonishing fidelity. A stepped platform above Lake Titicaca locks into right angles that seem almost machined. Polygonal walls in Japan flex against earthquakes with joints, so exact they disperse force rather than fracture. Monoliths in Baalbek rest in courses so massive they challenge modern lifting conventions. Circles of standing stones in Ireland hum faintly when wind moves across their faces, producing tones that linger longer than expected. These places do not share language, dynasty, or recorded contact. Yet their geometry speaks in recurring intervals, right angles stabilized beyond necessity, ratios that mirror harmonic relationships, alignments that acknowledge sky and cardinal direction with quiet discipline. The repetition does not demand conspiracy. It invites contemplation. If similar proportions appear again and again across continents and centuries, perhaps they emerge from principles embedded in the world itself, rather than from a single migrating blueprint. Resonance offers one such principle. Every material has frequencies at which it responds more readily to energy input. Wood vibrates differently from stone. Granite differs from limestone. Quartz within granite introduces another layer of response. When shapes are proportioned in certain ratios, they reinforce particular frequencies while damping others. This is not mysticism, but measurable physics. A chamber built with symmetric boundaries will emphasize specific wavelengths of sound. A mass aligned carefully to gravitational and seismic patterns will distribute stress predictably. Geometry becomes a mediator between environment and structure. Across continents, ancient builders appear to have favored forms that stabilize weight, distribute force, and sometimes amplify sound. Whether consciously articulated as theory or learned through repeated experience, the result converges, balance through proportion. Myth and measurement often occupy opposite ends of modern discourse, yet in antiquity they may have coexisted seamlessly. A culture that speaks of stones singing or temples breathing may not be indulging fantasy, but encoding observation within symbolic language. The vocabulary of vibration could have been expressed as ritual chant rather than Hertz values. The choice of certain sites near water channels or along fault lines might have been described as sacred rather than geophysical. When modern instruments record low-frequency resonances within ancient chambers, they translate into numbers what earlier generations felt through skin and bone. Myth becomes metaphor for experience. Measurement becomes refinement of that metaphor. Neither negates the other. Together, they suggest that ancient builders engaged with their environment through attentive listening, even if they lacked formalized equations. It is important to state plainly what this is not. The recurring geometry and acoustic behavior of ancient stone do not require extraterrestrial intervention. They do not imply lost civilizations wielding industrial machinery identical to modern factories. They do not demand rewriting physics. Instead, they hint at sophistication expressed differently from contemporary engineering. Human intelligence, disciplined through generations of craft, can produce outcomes that appear extraordinary when removed from their context. A guild that spends centuries refining stonework under consistent conditions may internalize principles that later societies, distracted by different priorities, allow to fade. Knowledge need not be technologically advanced in the modern sense to be deeply effective. It can reside in muscle memory, apprenticeship, and cumulative adjustment. Consider how geometry recurs not only in stone monuments, but in music, astronomy, and architecture across time. Harmonic ratios that define pleasing intervals in sound also define stable structural proportions. The relationship between base and height in certain pyramidal forms approximates constants that appear in wave behavior. These patterns may arise because the same mathematical relationships govern both acoustics and load distribution. When ancient builders selected dimensions that felt stable or resonant, they may have been aligning unconsciously with universal constraints. The Earth offers feedback continuously through vibration, echo, stress fracture, and seasonal change. Those who build in dialogue with that feedback refine their structures until harmony is achieved. Harmony, in this context, means equilibrium between mass and motion. Modern society often privileges written theory over embodied practice. If no text survives explaining a method, the method is assumed absent. Yet oral traditions and tacit knowledge can persist for centuries without leaving explicit documentation. Craft guilds may guard techniques as professional heritage rather than publish them. When political upheaval, economic shift, or cultural transformation interrupts continuity, such knowledge can dissipate rapidly. Later builders, inheriting structures without the accompanying subtle techniques, may replicate form without replicating nuance. This possibility explains regression without invoking catastrophe. Skill does not always progress linearly. It can crest and decline depending on institutional support and value systems. The idea that stone remembers is poetic, but grounded in physical reality. Materials record stress history in microfractures and crystalline alignment. Granite under compression responds differently than untouched stone. Surfaces shaped by repeated vibration may carry residual patterns measurable with sensitive instruments. If certain ancient sites were chosen and constructed with acute awareness of environmental resonance, their stones might still respond in ways that feel distinctive, not because they harbor mystical energy, but because their geometry interacts predictably with natural forces. Visitors often report a sensation of presence or vibration within certain chambers. While subjective, Such impressions may correlate with acoustic reinforcement or low-frequency standing waves that influence human perception. Balance between skepticism and openness is essential. Dismissing all anomalies as romantic projection impoverishes inquiry. Embracing every irregularity as evidence of hidden technology undermines credibility. The middle path acknowledges measurable phenomena without leaping to extraordinary conclusions. Resonance is real. Quartz responds to stress with electrical potential. Geometry influences vibration. Groundwater alters thermal behavior. These facts do not compel grand narratives. They provide fertile ground for careful exploration. When geometry recurs across continents, it may reflect shared exposure to the same physical laws rather than shared architects. Perhaps the quietest possibility is also the most profound. Ancient builders listened differently. Without industrial noise, constant artificial illumination, or digital distraction, they may have been more attuned to subtle environmental cues. The pitch of stone when struck, the way a chamber held a chant, the manner in which certain joints resisted tremor, these experiences could guide incremental refinement. Listening becomes an engineering tool. A mason tapping a block to hear its tone participates in acoustic testing, even if he names it differently. Over generations, such sensitivity cultivates structures that resonate not only physically, but culturally. Contemplation does not resolve the debate over drill cores or sarcophagi tolerances. It reframes the broader landscape. Whether cutting granite with abrasion or guiding it with weighted stabilization rigs, ancient craftsmen operated within a universe governed by resonance and balance. Their monuments endure not only because they are heavy, but because they are proportioned. The recurrence of certain shapes and alignments suggests that some designs harmonize more effectively with the Earth's rhythms. Harmony does not imply supernatural power. It implies compatibility. If stone remembers, it remembers through response. It vibrates under wind, warms under sun, cools at night, shifts microscopically under tidal stress. Structures aligned thoughtfully amplify or dampen those motions. The persistence of geometry across civilizations may signal humanity's repeated rediscovery of these compatibilities. Each culture, independent yet subject to the same planetary constraints, arrives at similar conclusions: stable angles, balanced mass, measured spacing, alignment to cardinal points. The recurrence feels less like coincidence and more like convergence toward equilibrium. A contemplative ending resists closure. There is no final revelation here, no definitive proof of forgotten machines or suppressed knowledge. There is instead a widening awareness that ancient achievements may represent a depth of attentiveness often underestimated. The sophistication might lie not in exotic devices, but in disciplined observation sustained across generations. In that sense, the ancients may have been less technologically advanced, yet more experientially tuned. They built in conversation with wind, water, and gravity. Standing within a granite chamber, one can imagine that conversation continuing. A low hum, barely audible, shaped by the room's proportions. Light grazing polished stone at an angle that reveals flatness achieved without lasers. The weight of blocks distributed so even that the time itself struggles to disturb them. These are not miracles. They are outcomes of sustained engagement with material reality. If geometry recurs around the world, it may be because geometry belongs to the world before it belongs to us. The quiet possibility remains open, that ancient builders listened carefully, adjusted patiently, and allowed resonance to guide refinement. Not alien intervention, not lost supermachinery, but an intimacy with matter that modern abstraction sometimes obscures. The stones endure, offering surfaces to measure and chambers to hear. They do not insist on explanation. They invite attention. In that invitation lies the softest conclusion. Perhaps the sophistication we seek was never entirely lost, only quieted, waiting in granite for those willing to measure and to listen at the same time.